Phillip Pilgram is the Subsea Business Development Lead in Nokia's North American region. He has worked in Subsea for over 30 years. Phillip is based in Nova Scotia, Canada. His father, great-grandfather, and great-uncle also worked in Subsea Telecommunications, so got a lot of experience there. Phillip has worked for Subsea operators, purchasers, designers, and suppliers, and as a hobby, he researches the locations of the early Subsea cables and finds them. So I've seen some of this content in the past, really, really cool stuff. So really looking forward to this. So Phillip, you all ready?
Yes. Thank you, Jason and Krista. And again, big thanks for inviting me to share my passion and my long career. And I guess to bond with everyone on this call, the very first submarine cable system I worked on was a coaxial cable. So it's nice to present to this society that works in that domain, because I'm very familiar with it. But and there was TV broadcast on that too back in the day. But anyway, I'll stop digressing and move forward with the presentation. I have a lot of slides, so we'll go through them, and hopefully you'll find it interesting, and perhaps it could even be something that you may need to refer to in the future, because a lot of these cables are not just in the oceans, but they cross lakes. And I had the opportunity years ago to work with Vermont Tel to help them get a cable across Lake Champlain. So here we go. Let me see if I can get my pointer up, because that will help a lot for this. So I'm going to go over these 9 sections, and it should go quite quickly. So as you can see from this, the Earth is mostly water. I think the formal number's 71%. So thus we have to communicate between the regions, and the need for submarine cables. So if you look at contemporary maps, you'll find that there's approximately 559 significant cables in the world. There's a lot of shorter ones too, like the one I mentioned in Vermont that wouldn't show up in these maps. And there's about almost 1,600 cable stations that connect these together. So some of them are data centers, but they terminate each end of the cable. So we'll go into the history of cables, and this is quite interesting, because I know a lot of the members on this call will be from the United States, and though the British wrote a lot of history, and anytime you see about submarine cables, you'll see the first one was from France to England across the English Channel, but that is not so. Right after the Baltimore-Washington connection, the very first submarine cable was built, and it was built by someone you may know, Samuel Colt, who improved the revolver. He didn't invent it, but he improved it, and went on to become very famous and very successful. In 1845, he started a company called the New York Offing Telegraph Association, and he laid the first cable across the East River. So if you look at this map, you can see the very first telecommunications system in North America was 1844, and it was Samuel Morse's telegraph line. And over here in New York, when they eventually built up, they had to get across here. So he laid the first cable. And this is a map from 1853. So there's all kinds of other telegraph lines here now, but you can see where the original ones are superimposed. Here's what his cable looks like. There were 4 conductors of copper, and they had a tar-soaked cotton cloth wrapped around them to protect them. And then they were placed in lead. This gray material is lead. And that again went across the East River. And if you do some research, you'll find these sort of dog and pony shows. You can see Colt's submarine battery. It's not an electrical battery, it's marine protection. So before he got into telecommunications, he was putting arrays of undersea explosives and blowing up ships using these cables with Samuel Morse. They shared each other's equipment. If you research, it's quite fascinating. And you know, they get 40,000-60,000 people on the Potomac River, or in you know, the south end of Manhattan, and the ships go over and Colt blows them up. so this is where telecommunications started. And if you read this article here, you can see you can go and get electrical shocks and things. Electricity was like the internet back then. So in 1901, here's a typical map, and you can see there's quite a few cables laid by then. They really started about 50 years before that. They're just starting across the Pacific, but you can kind of see the main routes here. And here's a contemporary map made to look old-fashioned. But if you superimpose the major routes, this is what I work with. So we have transatlantic cables, ones that typically go up and down the coast. You can see some here on the east coast of North America, again on Africa, and this is a common cable route too from Europe to Asia, but it will go through the Suez Canal, or sorry, across Egypt and down through the Red Sea, and trans-Pacific cables. But we're starting to see more cables up north. There's quite a few regional ones that connect Alaska, and they're starting to look at going through the Northwest Passage. And there always have been quite a few that went up into Greenland and Iceland too. So if you want to look at some typical cables, again, the very first one that I mentioned in 1945 was here in New York. Then they started building, and the big thing was to connect New York to London for business reasons. And that was the big driver. So in 1856, they put a cable in my region that went across here, the Gulf of St. Lawrence. And I've actually found this cable, and Queen Victoria communicated with President Buchanan on it. Then 1858, we're looking at the first transatlantic cable. It didn't last that long. It was new technology. It lasted about a month, but the proof of concept was good, so they continued on. It was all telegraph cables until 1956. Then AT&T and British Telecommunications can't remember now, the government of England actually were involved in this, and they couldn't do bidirectional on the same cable. They were coaxial, but it was unidirectional. And they called that TAT1, Transatlantic Telecommunication Cable 1. The very first fiber optic was in 1988, and that had two fiber pairs. One went to England and one went to France from United States. And then once Sonnet came up on us, TAT12 and 13 went across, and they made a ring, SDH Sonnet ring. So you have two cables here. So if you want to look at growth, this is the patch where I grew up and my ancestors worked in the transatlantic, basically connecting New York to London. They started the first one in 1858. It didn't work. Then you had the Civil War. So it wasn't until about 1866 that they really got going. So they're installing cables. Thomas Edison developed a way to increase the amount of signals on a cable called a quadruplex. So on one bare copper cable, you can have 4 people communicating on it, 2 at each end. So so they call that quadruplex, and then again it continued on until World War I. You see a lull there during that, and then the technology is changing now. They're getting ready to go from copper wires to coax. And of course, we have the Depression, World War II, and they don't really have the technology ready after the war. So the first one they tried was, I think, 1938 across the channel, but it wasn't until the mid-60s that they started really building them. There's an early one to Cuba and, of course, transatlantic. And that went on until about the 1980s, the late 1980s, when they started with fiber optics. And you see significant growth here. You can look at the slopes, but there's huge growth here. And this is around 2000, the dot-com boom. And you can see the result of that. It killed the industry, so we were dormant for quite a few years, but we're back into it now, and the industry's growing. And these are the number of cables that were built. So you can see here in 2000, it was huge, and then the lull afterwards in this little inset. Also too, to consider, like around this time, like it affected everyone, but we were working with 2.5 gigabit per second waves, and it jumped to 10, so it's 4-fold increase. And this technology called DWDM, where you can put many signals on the one fiber, happened, and also data compression too. So we're going up into the dot-com boom, all these, you know, I guess projections on how much data we're going to use, but then the data gets effectively compressed, and the channels that we have set up can carry more data. So the big lull. And quickly go over cable types now, and who owns them, and how long they've been working for. So basically, what we call web scale at Nokia would be, you know, your Googles, your Facebooks, Microsofts, Amazons. They've only been in subsea cables for the past 10 years, but they've been driving it like crazy. Before that, probably for the past 20 years during the dot-com boom, a lot of independents came into this, started working. Global Crossing was one of the first. And then before that, it was always governments. Everything was regulated, so they would set up consortiums or set up their own cables, and that's been going on for about the past 50 years. You still see some of these operators. The oil and gas industry, they use submarine cables quite a bit to connect their assets. The energy sector, of course, you're seeing a lot of offshore wind and electrical connections between islands. That's been going on for a while, but they have special cables. Scientific community now, they have cables, and they have some interesting aspects of them too, because they can change the payloads underwater in quite quickly. And the United Nations, they have submarine cables, and I've got an insert for that. So basically, this would be, say, an island, and you'll see the submarine cable go out, turn, and then stop. So it's a very strange cable, but what they have on this are they have these hydrophones that listen. They'll have a triode of these. There'll be 3 of them, or triad, and they're for directional listening of sounds of nuclear explosions. So there's something called the Comprehensive Test Ban Treaty Organization of the United Nations, and they're sniffing the atmosphere for I guess ionized gas or radioactive particles, and they're listening for seismics, but they're also listening in the sea because there's a natural wave guide at 1 kilometer down where sound will travel across an ocean. So these things, sadly, they will pick up horrible things like implosions of submarines and that, and they've done that before. But this is something that very few people know about, but it's a special type of cable. And with the oil and gas industry and the scientific industry, these are robotic arms from an ROV. It's probably a camera unmanned, but you can actually plug into these. They're called wet mate connections. So you can actually mate fiber optic connections underwater, and they will work fine. So so this is a unique, I guess, feature of some of the cables that can be exploited. If you see here, you can see Houston, Baton Rouge, and New Orleans. I'm sorry, this is a very busy map, but the blue line here is the submarine cable for the Gulf of Mexico assets, which are all these dots. I'm not sure about these red lines. They may be supplementary cables that were eventually laid. The backbone would be this long one, and then they have 4G radio when they're showing areas around for the radio on this map too. But this was one of the first oil and gas submarine cables used in the industry. My old boss actually designed this, Steve Lentz, a brilliant guy. And anyway, this was cookie cuttered, and it's in the North Sea. It's off of Australia, off of Brazil. They have you know, off of Africa. They have this now in the oil and gas patch. So types of cable systems, topologies, the typical one would be point to point, but you can also get a festoon. This is not a good example, but basically you'd have one cable that goes to a site and then a totally different cable that goes to another site, and you just link down. This can allow you to have shorter cables that can cascade it together. This one's actually trunk and branch, but it's in the shape of a festoon. And then you can have unrepeated. So this is around Toronto, Ontario, and it goes down to, I'm not sure what city this would be. I think Buffalo's up along here, Rochester on Lake Ontario. But this one would have no amplifiers in it at all. You blast light in one end, it will come out in the other end. The longest cable currently being installed, they're a little behind, 16,600 kilometers. So it connects Los Angeles to Singapore, and it has some branches that go to the Philippines, Guam, Indonesia. You'll find now there a lot of these would have gone to China. Typically they went to Japan, then there's branches to China, but there's some issues now, so there's a bit of avoidance of that area. So you're seeing these longer ones go deep into this area, and it also avoids the South China Sea, where there's a lot of aggression and fishing now that will cut your cables. So 16,600 kilometers. A short cable, this is the one I mentioned earlier in Lake Champlain. This would be Vermont Tel, and it's just a very short one. There's actually a ferry you can see right here that goes parallel to this. The largest cable system in the world, it's just being completed now. It's called the Two Africa cable, and it's the cable itself. It starts in England, goes down the coast of Africa. There's a branch to Portugal, goes around. There's another extension to India, kind of comes up into the Arabia Gulf, again up through the Red Sea and through the Mediterranean. There are many fibers on this cable, so there's far more than 45,000 kilometers of fiber that's used. But to give you an idea of what it's like, the Earth's circumference is about 13,000 kilometers. So to scale, I drew this tube, and that would be 45,000 kilometers. And the circumference of the Earth is 40,000 kilometers, so you could wrap this around the middle of the Earth at the equator. So now we'll look at some of the components. What do you need to build a submarine cable system? This is a very busy slide, so I'll try and go through it in a in a logical way. So the very first thing I step down here is transmission. So you need terminals. So these will be the optical terminals. In terrestrial, it's called a line terminal equipment. In subsea, we usually just put an S in front of it. So submarine line terminal equipment. So SLTE is a very common acronym. That connects to the fibers and sends your signals along the cable. But of course, you can only go so far in fiber, so you have to amplify the cable. So we have these amplifiers, which we put in these housings. We call them repeaters. They're actually amplifiers. They don't regenerate like a repeater would, but it's just a name that's stuck. And we have to power these electrically, so that will bring us back to a power conductor in the cable and our so-called power feed equipment. And again, this stuff is dangerous. It's like a high voltage system. You can get up to 30,000 volts potential difference, and it's death on contact. So it's very serious business. And especially if you're repairing a cable and you're testing it, you know, someone could be on a ship with their hands on this copper, and if you turn it on, you can electrocute them. So there are all these interlocks and safety protocols for powering up systems during repairs. We also have to monitor the system and see if there's any optical or electrical faults on the system. So we call that a supervisory system. The typical acronym is LME, line monitoring equipment. And of course, with any telecommunication system, you have to manage it all and present it to a NOC or engineers to work on. So you have element management systems, network management systems, operational support systems, and they're connected to all these subsystems. So that's basically the main components of a submarine cable system. Now, if you look at the cable itself, what we're interested in is the core here where the fibers are. Then we have to protect those. So it's kind of like being inside a tank, a military tank. So you have all this armor around you. We actually call it armor. So the first layer of protection is a steel tube. And what's interesting is that we put this special, it's called thixotropic gel in this tube. So if the cable does get cut at very low, deep depth, all the pressure of the water won't shoot in here and wreck your whole cable. So the gel actually, when it meets water, it expands and it will seal it. So you only have to worry about water penetrating at the bottom of the ocean. It's typically 6 to 8 kilometers. It'll only shoot back about 1 kilometer. So if you do get a cut, you just have to stub off the last kilometer of the cable, then you're good to do your from that point on. There'll be steel strength members around the cable to give it strength. And then it's kind of hard to see, but there's copper here. It's basically a copper tube that's helically welded, and that's our conductor. And you'll be shocked, this can have resistance of less than 1 ohm per kilometer. So we use electrical methods to find faults, but when you're dealing with like less than 1 ohm per kilometer, if you're off by 3 or 4 ohms, you know, you're 5 or 6 kilometers away, so you could send the cable ship to the wrong location. So we had to be very accurate if the cable has an injury and we can't use optical methods to locate the injury. This is basically like a skateboard wheel material. I think it's polyethylene cross. I can't remember the organic name for it, but anyway, sorry, so many acronyms. And then once you have this core that the whole submarine cable system is built upon, you'll put different layers of armor. If there's one layer of armor like this inner one, it would be called single armored. In this case, it's 2 layers, so we call this double armored cable. Again, the electrical insulation, the armored wires. And you have this basic core, and we wrap things around it to strengthen it, but the basic core is through all the types of cable. So this one has a light mesh. The name for this is shark bite. Those sharks do bite the cables. They're not an issue. It's sensationalized, but it's more for abrasion. Single armored here, a thicker wire here for single armored, a double armored, and this is a heavier double armored cable. So that's how we protect it. This cable is very light, so you can drop it off a ship. You know, it's qualified to 10 kilometers depth. But it gives you very little protection. But at that depth, you know, there's very, very even few sea creatures around. But as you get closer to the shore, you'll protect it more from ship aggression. It's heavier cable and it's very well protected. So this is the repeater, the amplifiers that I showed you. It's basically like a submarine. It's a sealed off vessel. High pressure, of course, it can take. It has, we call them gimbals here. You can move these things in X, Y directions. There's bend limiters on them, big rubber tubes for protection on the outside, but underneath you'll see like a mechanical gimbal there. You can make them from titanium, steel, copper, beryllium. If you ever see the word copper beryllium, run away. That stuff's very toxic. You don't want to breathe it in, but it does offer good corrosion resistance. But steel with paint over it has worked great for years. The optical amplifiers are in these. They're designed with very low failures in time. I'll throw out the number 16 if people are familiar with this. They're just made to last. They're designed for being put in the water and running for at least 25 years without any type of maintenance at all. They're typically spaced from 10 kilometers to 120 kilometers apart. 10 kilometers would be the older cables. 120 would be if you're trying to save money and you don't want to spend any money on amplifiers. They're quite expensive, so you can save costs. Typically 1 fiber pair to now 24 fiber pairs. That's very low compared to terrestrial cables, but for subsea, there's a lot of electrical aspects. You have to power these and you have to put the amplifiers in, so we can't go to the high quantities of cables, fibers in a cable that you see in terrestrial. They're qualified to 8 kilometers. I said 10 earlier, it's my error, it's 8. And they're insulated to 15 kilovolts, and the industry is moving now to 18 kilovolts to push it a bit more. But in the same time, the lasers for the optical pumps have to be cooled, so you have to get through that electrical insulation. So there's to get to the outer wall of the amplifier to give you any cooling for your electronics. So there's some clever techniques for doing that. Now, this is a big problem, is that the cable is largely, as you know, with coaxial cables, it's a large coaxial capacitor. So if we put 15,000 volts on this capacitor and it gets cut, that will discharge quite quickly, and you can get upwards of hundreds of amps. These are qualified for 500 amps blasting through them before you have significant problems, but it can be an issue. The pumps inside, these are erbium doped fiber amplifiers. That's basically your amplifier. There's an optical coupler here, and you'll have 2 lasers, typically 980 or 1480 nanometers, that are injecting into this optical coupler, and it splits the output for redundancy to each of these EDFAs. So if one laser fails, you still have another laser pumping. You'll have a 3 dB loss because you lose half your power, but it will still feed both amplifiers. So resilience is the primary design aspect for submarine cable systems. You don't want to have to go down and repair things. It's like going into space. So later on, around the year 2000s, they used different pump architectures, and here's an example. There's many of these. Here's a 4x2. But this is what's current. We call them pump farms. So if you had 24 fiber pairs, you'd have 24 pumps. And you go through these combiners and splitters and combiners. So effectively, pump number 1, and you have 4 pumps, 1/4 of the power, if you follow these lines, is feeding all of these 4 fibers. Pump number 2, 1/4 of the power that's feeding every one of these is coming from that pump. So you maintain your ratio of resilience. Again, some more pictures here. This is a different type of submarine cable in that the core here is not steel, it's plastic. There's different philosophies on what you need in a submarine cable, but effectively it's the same, and you can see the armor here is a little closer together. Here's a cable ship. Of course, it can't get close to the shore, so they use smaller ships or barges, or quite often they'll have divers and they'll float the last piece of cable in with all of these balloons. Sometimes you can't bring the cable in like this. The ship will be a kilometer away, and they'll have directional drilling, which you're probably familiar in terrestrial networks. So they'll horizontally drill out a kilometer, and they'll have some pipe that they'll feed the cable in and pull it through to the beach. This is inside a contemporary cable ship where you have all the cable ready to go. And this is the very first one. Not much has changed. You know, they have gas lights here and fancier hats back then. But effectively, you know, it's a lot of manual labor to do this, and you're talking thousands of kilometers of cable that goes in these ships. So it still seems to be old-fashioned in this sense. Here's some more pictures of the repeaters. Here's one either being pulled up or deployed at a shallow angle, and you can see here they call cantery, where the ship's laying the cable, but it's touching bottom, maybe 5 to 10 kilometers behind the ship at angles like that. Here are these guys manhandling these repeaters, and these are the copper beryllium ones, the dangerous ones. And this is what's inside a repeater, more details. So you have your pumps, your combiners, more combiners. Your optical signal comes in on a fiber, and then it goes through this special erbium dope fiber, which is excited by these pumps, and it gives you the amplification. A gain flattening filter will equalize the system, then it will come out again. So in the reverse direction, here it is. This is a special type of repeater. It doesn't necessarily have to have amplifiers in it, but you can see there's a main leg here and there's two that break off. So we call this a branch. Electrically, you can have the power feed equipment that I spoke of. Here's 3 cable stations. There's a branching unit here. The symbol for it's a triangle. So this could be the main trunk and this could be a branch. And then you can have optical devices in the branches too. So you can have a fiber go through, and that same fiber could be connected to the branch and the trunk. So you can have what we call ROADMs there, where you can electrically select what wavelengths drop at these sites. These could be islands, and this could be mainland here and mainland over here. Or you can have passive filters in these as well. A gain equalizer, again, I just mentioned that, but in EDFA, if you just have a raw amplifier, it won't give you a flat output. It'll be peaky in a few parts of the spectrum. So the gain equalizer filter is almost an inverse of that. So if you have this raw amplifier and you equalize it with some optics, you can get a nice flat output across the spectrum. And you can have active ones too. So they're generally in these smaller housings for the equalizers compared to a repeater that's a lot larger. And you can actually tilt the system if you have to tilt it. You know, we're working in infrared, so in the middle of the what we call the C bands, typically around 1550 nanometers. So here's an example of a tilt of this system using that. This is what a power feed looks like. Again, there's interlocks here, so you can't go in and touch anything and electrocute yourself. So by the time you the way the interlocks work is that you have to hit a switch, then it gives you a key. Then you use that key to plug in and turn another switch. So by the time you get the switch to open the backs and get in these to do maintenance, you've effectively turned it off. So there's this is a working on one side, a protection on the other, and a common unit in the middle here. So we power, this is across the submarine cable system. So one power feed at one end would be, say, a positive voltage, the other one would be a negative voltage. So you could go plus 15,000 volts here, minus 15,000 volts. So across the cable, you have a total of 30,000 volts. And we leverage the earth as a return path. Every electrical circuit has to have a loop of current. So one power feed will power the copper conductor of the cable, and it will go to we call it an ocean ground, but it's just a ground at the cable stations at each end. So the resistance of the earth is considered to be 0. So we leverage that. We get into trouble though. Recently, we've seen a lot of northern lights, but solar weather can affect these submarine cables. For example, localized magnetic storm over, say, Europe can drop the voltage, the earth voltage here, by 1,000 volts. So the power feeds have to compensate for that, and if they can't, it will shut down. And this is what an ocean ground looks like at the beach. They'll basically have these anodes, and they're all connected together, and they put sometimes it's just called coke. It's like a graphite type material that's conductive, and you can see here it's like a phosphorus type volcanic soil, beach soil and that. So they're trying to get a good ground connection here from the power feed to the earth itself. This is I think I grabbed this. This is an NEC from Japan, one of their terminals. And in that terminal, pretty much every terminal, you'll see submarine cable, you'll have booster amps to get out to that cable, the launch into it. A multiplexer, your transponders would be your modems, and on the receive, the signal will come from the cable, and we'll boost it with an amplifier to push it through a mux, which would have some loss, and then feed our transponders. So very simple architectures in the terminals. And this is the one, the coaxial one that I trained on years ago. And this slide, it's a company called STC that built this back in '73. And I was showing the history of Nokia back to that point. So it was called Standard Telephone and Cables, which started in 1883. And they were actually sold to Nortel in the 80s. And then Nortel sold it to Alcatel in 1994. And then our company that I work with, Nokia, bought it. in 2016. So that's the path of it. And again, this cable was 1973, and the bandwidth of it was only 14 megahertz. So the lower 7 megahertz went from Canada to England, and the upper 7 megahertz, from 7 to 14 megahertz, went from England to Canada. And this is what our SLTE looks like now. You can take it on a plane. So basically everything's done on this one blade. This is a multi-degree ROADM, but it's an SLTE on a blade rather than a full lineup you just saw. This whole thing, including the fiber breakouts, is only 31 pounds, 19 inches, 5 RUs high. You can make it into a multi-degree ROADM too. It's generally not used on the subsea side as a ROADM. We have some installations where it is, but generally on the backhaul, you'll have 2 or 3 diverse routes back to points. So this can be used for subsea and terrestrial. You can use it for restoration, say if your cable breaks and you have to put your traffic on another cable. If you have to do spectrum sharing, where in the optics now, usually you'd buy lit service, say, 1 gig, 10 gig, 100 gig, 400 gig, service. But now you can actually buy part of the spectrum on a fiber, and you can put your own equipment on that. We call that spectrum sharing. Noise loading, it's kind of funny. Submarine cable systems are designed to self-heal. So if you get some loss in the wet plant, it will actually increase the gain of the amplifiers to compensate for that loss. But because of that, they're always trying to push to a fixed output. So if you put no signal into a submarine cable system, all the amplifiers are going to go crazy and just go to the rails and try and boost anything that's coming in. So what we have to do is we have to make sure that the transmitted signal into the submarine cable is always there. So we have to have a full spectrum sent into that. So we call it noise loading, where you have your traffic signals, but where you don't have traffic signals, maybe future ones will go there, we have to put dummy channels, and we just use ASE noise to make these fake channels to load the system. Open cables, that's a recent term. Open cable just means anyone's terminal equipment can go on a submarine cable. Years ago, the suppliers of the cables wanted to ensure that they had continued sales, so they would just say you have to keep buying your equipment from us. But that has changed; it's more open now. So the cables are agnostic. And again, these SLTEs now, they'll work with repeaters and unrepeated systems, and you'll have supervisory too. OTDRs, which you're familiar with, we call it coherent. This was before coherent transmission, but COTDR is used in subsea, where we can actually see through the concatenated repeaters, and we can see every span between them. This grim slide, if you ever go down to an ocean and look at it and just think about, my gosh, there are cables out there underneath that, like what the heck's going on with these things? They're subjected to so much environmental aspects, man-made aspects of aggression. So we have something called supervisory, so you can actually see what's going on with the submarine cables. So again, on the old submarine cable system, now the supervisory section is over here. And it was used, a passive method was used then. We just send a signal out and it loops back from every amplifier. And because submarine cables are so-called like a cookie cutter design, you can every span can be manufactured in the factory to the same length. The amplifiers can be identical. It's quite easy to leverage these loop gains. Back in 1973, when this equipment was first installed, it took about a week to check all the amplifiers in your system. And then by 1980, I first worked on this in 91, but 1980, Hewlett-Packard came and they made an automated test set. So you can do it in about a day. You can measure all the 400 amplifiers. Around 1995, with optical systems, AT&T submarine systems, it took about 8 hours on the first SLTEs that they made that were optical. They're called SL2000s. And during the dot-com boom, it still took about 6 to 8 hours to check out your wet plant. But recently, I'm working with some colleagues now. It's kind of fun. They have this new technology, and almost in real time, you can see the whole wet plant. So we're doing a lot of trials on this now, but it's come a long way. So automation and technology now has made submarine cable systems more manageable. And again, this is what you have to do with the supervisory is on board a ship. They have to do all these fiber splices. So what we have to do is we have to power up the cable. High voltage goes through this, so he'll be hands off at that point. We had to validate all of these fiber pairs. So supervisory will do that too. So the loop gain concept, this is a crude analogy that I've made, but if you can think of, 3 mountains in a row and you yell hello, your signal will go out and it will reflect off the first mountain, the second mountain, and the third mountain. So this is basically what we're doing with subsea supervisory. We have an amplifier here and a high loss loopback, sorry about that, and a high loss loopback, which takes your transmit fiber and at a very low level, it taps it and sends it back to yourself. So you're gonna have this signal come through. And say the repeater spacings here are 100 kilometers, the signal will go at 100 kilometers, loop back, another 100 kilometers, loop back, another 100 kilometers, loop back. And if you look at all the rises and falls in the gain, all of these signals should come back at the same power. If they come back at a different power, something's happened between the first loop and the second loop, or the second loop and the third loop. So if you install a submarine cable, it takes a long time to do it. So the first phase is about 2 years. So you have to kind of look at, okay, we want to do a submarine cable. What are we going to connect? What are the issues here? Quite a few of them are permitting, dealing with fishermen, no lay zones because of marine sanctuaries, natural hazards due to earthquakes, buried ammunitions after World War I and World War II. A lot of ammunitions were thrown off vessels where I am here in Eastern Canada. So you can't go around those areas. So that typically would be done as well as the permits. They would often do a marine survey too with side scanning sonar to see what's down there and make sure it's a good route. Then you get your permits. Then of course you have to do the design of the submarine cable system once you get the route in that. So there's a lot of undersea GIS type mapping on where they're going to lay the cable, the depths and everything. And then you have to manufacture the cable. It takes quite a long time to manufacture the cable. You have to get the raw copper, you have to get the steel, you have to get the polyethylene. So you run it through there, and typically about a year to construct it, or within a year, depending how long the system takes. The 2 Africa 45,000 kilometer one is about a 2 year to build it and get it all out there to the sites and install it. So then of course you have to get the ships to go from the factories to the locations. You may have a factory in the Atlantic, but the cable may need to be laid in the Pacific, so you've got to traverse over there. You've got to do civil works too. I mentioned directional drilling. You may have to build some cable stations. Also too, like I said, fishermen, you may have to appease them and pay them a lot of money so that you can compensate them for disrupting them, say during a fishing season if you're laying near a beach. And then once it's installed and commissioned, you have to run the system, and they're designed for 25 years. And while it's running, if there's a fault, you have to locate the fault, go out and repair it. You have to, expand and add modems to get more services on the system to make more revenue. So that's basically the life cycle of a cable. It's a very long process, very expensive too. So other aspects of owning a submarine cable system, and that would be, again, the risk. You want to mitigate that. You have to protect it, you have to power it. And again, these are mega construction projects. So here's the very first submarine cable system that was built in 1866. In June 1867, they actually saw the iceberg coming. They watched it for a week, and it rode right over the cable. So this is a piece of the damaged cable from that point. So this is an old telegraph cable. And again, for mega projects, you have all these ships that are specialized for laying cables. The burn rate for these is about $120,000 a day. So it's very expensive to send ships out and repair cables. This one, I'm going to show you another slide, but you can see there's a human here, and this big fin-like device blows high pressure water into the soil, and the cable will be laid deep under the ocean surface. This will get you down, I think, around maybe 30 feet, 20 to 30 feet. And if you don't have soil that you can blast away, you have to cut it first. So this is a big rock cutter, and again, you can see the size of it relative to these guys. So something like this would be used in a rocky harbor, say if you're bringing a cable around New York City or something like that, or Baltimore, where there's a lot of activities. And again, this is using the power feed equipment. This was a medium voltage, it goes up to 6 kilovolts. They typically go up to 15, up to 20, and you can operate them from a front panel. But again, to get in behind this, you can open this door here, but there's interlocks with keys to get to the dangerous stuff. And again, a repeat of the earth return. A quick shot of a cable ship. You can see they have thrusters on the back and on the side here. So these can hold position when they're in a storm and they're holding a cable that may be 8 kilometers down. You don't want this thing drifting around, so it has to move forward, backwards, left, and right. You can see the cable tanks here. And it can be very dangerous too, because you know, when you have the cable on board the ship, if the weather gets bad, it can be jostled around. The cable can actually, you know, damage things. So quite often they may have to do a cut and run. You can see there's a buoy here. They would tie that to the end of the cable. And this is a sea plow here. When they lay the cable, this will bury it up to about 1.5 meters in the water, this contraption here. It looks like a sled. They tow it behind and the cable goes through it. So I push on quickly. Again, some more pictures of these devices. And here's plowing the cable into the ocean floor. So you have a high tension tow line here, and you have an umbilical that goes down so you can read the pressures on this sensors. There may be some hydraulic or electrical devices here to lift it up or down a bit. And then the submarine cable will feed into it from another entrance.
Hey,
And
Phillip, I got
yeah,
a question for you. So that big chainsaw looking thing, is that actually pulled underwater? That all operates underwater? Or
yeah, it's usually shallower water. So you can see here's a barge with a crane, and you can see this one's is dropped from a crane here. I don't know if you can see there's the crane structure here. So I assume this would be the similar. I've never seen one of these in action. I've been on board the vessels. I've seen the plows and the ROVs, but these are very specific, and they get you down. So you would see these deployed, like say Hong Kong Harbor, or you know, off of Mumbai or places like that where there's a lot
yeah.
of shipping activity. But yeah, I would say probably a crane or something really hefty to get that down.
Wow, that's cool. Thanks.
Yeah, no, excellent question. Yeah, so you know, I was involved with Lead Corps, and they did a lot of you know, things like this on the railway line. So they would do a survey. They would use rock cutters where there was off a railway car, and they would cut through the rocky areas along the railway lines, and then they would go through and they would have something where they could push away the rock they've just chewed up, and lay the fiber optic cable on terrestrial. So it's the same sort of principle with this, because even though you chopped it up, you've got a lot of debris in that trench, so you're probably going to have to go with this and go into the same trench and clear it out and lay your cable in there. Now, of course, if that cable does have a problem, it's it's no fun to have to get back down there 30 feet under the rocky surface to pull it up. You know, they may just go, you know, a few kilometers on each side and you know, cut it out and put a new piece in. So it's very troublesome when you put something that far down under the floor. So again, that first cable that I showed you from 1973, there were about 10 miles of this articulated pipe. It's like a suit of armor, and this would be like the cuff, you know, on your wrist. It's about that size. You can see this guy showing them here. They clamp together, and then you bolt them together. And here they are on the bottom of the ocean, and the guy's literally walking on the bottom installing these. So it's good revenue for divers, not in deep water, but we can't bury the cable. And sometimes these are actually bolted to the ocean floor too, if it's really rocky. So we call this articulated pipe or split pipe. There are newer designs now where they click and lock, so you don't have to use the bolts. So it saves a lot of labor. But can you imagine doing this for 10 miles? But it's done. So this slide, I'm just showing you, I'm going to show you something kind of cool in a second, but these lighter blue areas, that's the continental shelf, and that's typically to a depth of 1.5 kilometers. So that has to be buried with those plows, and when you get closer to shore, you know, you may use the articulated pipe. But you can see over here in Europe too, if a lot of the submarine cables leave here and lands in, and they go all the way out through here. So there's about, I think it's about 800 kilometers that you have to bury the cable. Whereas if you come off here in New York, you know, you go to a couple of 100 kilometers and you're into the deep water here. So you don't have to worry as much fishing over here as you would over here. I'm going to digress a bit. Now, sadly, we all saw last summer this tragic ocean gate, you know, viewing the Titanic, and they couldn't rescue them. But this happened 50 years ago, again on that same submarine cable system that I had first worked on, the Cantat 2 cable, where I showed you the terminal equipment. So back then, they didn't really have the sea plows working very well. They were developed in the late 50s, early 60s. So they had these devices, which had, if you look over here, you can see there's 2 men in them. So it's a man submersible, and these would go on the continental shelves up to, I don't know what their depth, it wasn't quite 1.5 kilometers, but they would go down and they would use jets, and they would jet in the submarine cable instead of plowing it in, or where it couldn't be plowed, they would go down. So they would go down for, I think it was a 12-hour period, then they'd come back up to the ship, and another crew would go in and they'd fix it up and send it down. So very similar in design, but you can see they're in a sphere. So they're in this protected sphere here rather than this elongated tube. But anyway, they ran into trouble. It was in August 29th, 1973. They're off the coast of Ireland. Again, a 2-man crew. So it's called post-lay burial work is what we call it in the industry. And they're at a depth of 500 meters. And what happened was they were trying to bring this up. There was some hatch back here that was opened. They almost had it on the ship. Then the hatch flooded. And then it just sank them to the bottom. And you can see here where it's stuck in and cracked. Then they hit the bottom at 40 miles per hour. And the poor guys that were in there, there's actually a book about this. They knew they were falling, so they prepared themselves for hitting the bottom. And they got stuck in the bottom. They couldn't get out. They had 64 hours of oxygen left, but they were able to stretch it to 84 and a half hours, I guess. So on September 1st, a few days later, they did do the rescue. And you can see here, this device is the Pisces 2, which they got out there. They dispatched, I think it was in, here's the Pisces 3. This is the one that they brought up and rescued. Here's the 2 guys here. And of course, in the 70s with all the bushy hair and the cool coats they wore back then. They also, besides getting this, I think it came from Bristol, this one they got at the Pisces 2. They also brought this thing over called the Curve 3, which is an early prototype, and I think it was from San Diego, or it's sort of a military device, an ROV device, but they brought that over and flew it over to get down there. So they had 2 of them down there doing the rescue, but they found the Pisces 2 worked a little bit better than this remote one. They had some issues with it. And the cable ship was called the John Cabot, which is actually, it's kind of funny, it's an icebreaker. So all this happened. It says when they got them out of here, they only had about 12 minutes of oxygen left. So it was a happy story. Again, the Cantat 2 cable. And here are the 2 guys here, Roger Mallinson and Roger Chapman. Actually, I'm gonna go back once, and I thought there was a picture of the book here. Yeah, this is the cover of the book. So Roger Chapman, he wrote the book called No Time on Our Side. So if you want to read that, it's quite interesting. And so we'll look at now operations. I think, I should get moving with time. So submarine cable system designed for 25 years from what we call beginning of life to end of life. Faults are going to occur. Usually it's fishing. Sometimes you can have some bad luck with the geology in the area. The tsunami and in Japan took out a lot of submarine cables. Marine activity, of course, ships and vessels, anchors, and of course component failures. Unfortunately, that can happen. It's very rare, but you can have something like that. So if you look at this strange event here, I don't know how well you can see this, but this kind of dark area that's eroded here in the sea floor, it's flat, and then you see this anomaly, that's coming from outflow from the Great Lakes over thousands and thousands of years. And it deposits a lot of, it erodes the ocean floor, but there's a lot of silt here. And in 1929, that let go, and you can see the outflow here. This is all historically over the years. You can see it along the shelf, but right here, a lot of this would have been debris that flowed out in 1929. You can see here, this is a historical map. It's showing about 1 kilometer to 4 kilometers depth, and you can see a lot of the submarine cables going along here. So a lot of the submarine cables that came up from New York and Boston went along here, and they came into Newfoundland where they regenerated and they went across the Atlantic. There are also ones from Nova Scotia that went along here and went across the Atlantic. So in 13 hours, it took out 12 cables. So this flowed, and you can see there are cables down here that were taken out too, and they're 500 kilometers away. So way down here, some submarine cables happen. So you can have some bad luck. A few years ago, they caught this on videotape with scientific instruments off of California. And off of Africa, this happens all the time at the outflow of the Congo Canyon from the Congo River. So the nice thing with submarine cables, they're kind of marine sanctuaries. They're generally, it's not always enforced, but there's generally a 1 mile exclusion zone of no fishing on each side of a cable. If you own a cable, you're going to patrol the routes. We used to fly planes over them every Friday, and if there's ships on the cables, here I am in Nova Scotia, and a lot of the cables went out here. If there's ships on the cables, cable routes, you'd radio them and tell them to get off them. We had one instance where our cable broke. We dispatched the plane, and they could actually see the ship with the cable on board the ship. They'd pulled it up with their fishing gear, and it was a big ship. So operators too, they're going to have to do upgrades when they start running out of capacity. And if there's new technology too, years ago we used to have on-off key 10 gig technology. Now we're using coherent transponders. Repairs, you're down for a long time, 1 to 3 weeks typically. So you have to get your traffic restored. And protection, do you do it at layer 3 with the routers, layer 1, which would be, you know, SONET SDH type, or layer 0, which would be optical and routing your signals away. And then years ago, they used to have cable and cable restorations. So there were agreements between the various operators, even though competing for customers, they would have these friendly agreements. That's coming back into play now. When the business group took over for the last 20 years, they kind of said it wasn't needed, but it's becoming needed now. So there's limited bandwidth on submarine cables, and the growth is crazy. Typically, in the worst case scenarios, it's 20% compounded annual rate of growth. So that means that the traffic is doubling every 4 years. And for a submarine cable system, you're going to invest a minimum now for transoceanic about $300 million, and you're getting price erosion. So even though you're getting the growth, you're getting erosion of price. Here's some faults, just a friendly little picture of a shark taking a nibble on this. Again, there's historically no cable that was ever damaged by a shark, but you put anything in front of some sharks, they'll take a bite at it. Again, this is the one that was damaged by the iceberg. This is what it looks like when you pull it up on the ship when the cable was damaged. This is on a repair ship. It's just the wiring around it just goes sprung and it explodes. And here's a picture of an anchor that was cut, probably broke off. But you know, when they're trying to recover their anchors and that, they can really damage the cable. This battle, the cable obviously won. So we can have shunt faults where just the outer armor of the cable is damaged and that copper conductor is exposed. So it's an electrical fault, but a cut will cut your fibers and then you can't operate. You can of course have equipment faults underwater. Typical causes: fishing, shipping, marine activities, geological, and other. I'm trying to think now what I meant by other. I'll let that one go for now. Give me a pass. Take a mulligan. Here's some data. So 95% of all cable faults are due to external aggression. Very little from manufacturing defects. And again, they have other here. So. So if we look at the 95%, 45% fishing, 25% anchors, and 10% geological. This was global data, but if you go to, say, an area in the world, if you go in the South China Sea, it's almost 100%. When the Chinese fishing season's open, they just go out and they chop up everything. In North America, we're kind of lucky. The fishermen kind of stay away from the cables, and we usually get shunt faults. We don't get complete cuts. Usually it's accidents. So what do you do to deal with faults? So you have to detect that the fault happened on the cable. You have to locate where is that fault on my cable. You have to dispatch a vessel to fix it. They have to go and recover the cable from the ocean bottom. And then once they have it up on board the ship, they have to see is the fault nearby, because they may be a few kilometers away. So they've got to locate the fault accurately. Then they have to go to that location and repair it. They have to replace some of the cable. And then the shore ends will have to test the splices that the ship made. They'll close it all up, put it on the bottom of the ocean. The shore ends will validate the end-to-end performance and release the ship. And then you have all these baselines for your supervisory that you have to update. This is a conceptual drawing of 2 submarine cables. And this one you can see where there was a repair. So 2.5 times the water depth of extra cable is added because the cable's laid on the bottom of the ocean. If you pull it up from a ship, it's like pulling a crossbow or any type of bow. You just can't do it. So you have to cut it, pull up the ends, splice new cable to that, and find the end that you buoyed off and tie it to it, and you just don't let it fall to the bottom and turn into a big mess. The ship actually goes perpendicular to the cable and lays it down in a nice orderly fashion. So you get this sort of horseshoe type effect where there was a repair. Again,
Sorry to interrupt. Just a
oh,
little time check. We have about 5 more minutes. I know we got off to kind of a late start, so apologies for that. And I know you have a lot of great content, but about 5 more minutes if you want to decide what you want to go over in that time.
yeah, that's fine. I'll just blast through it really fast.
Thanks.
The alarm indication signal, identification signal. Any of you that worked with old DS3s that years ago, it's not all ones or the yellow signal. It shows you where ships are. And this one I just checked this morning. I'm up here a little bit is where I'm located, but this is the nearest ship to me. So you can go to these sites, and this one's called Vessel Finder. You can see the ship. It shows you where it is, and it shows you the track of the ship and where it's going. So these are techniques now that help us when we have a fault. You can identify what caused the fault in that. And here's a shot this morning of all the ships you can hit across the Atlantic Ocean. If you go into New York Harbor, you'll see hundreds of them. So so this is the new AIS that we use in subsea. Testing. I'm going to bypass these slides. I'll teach you something though. We'll go past this. So I'm going to bring up all this slide here now. So in communications, you would deal with this. We call it optical signal to noise ratio. So of course, if this is a wavelength here, which is this curve, there'll be noise underneath it. But in optical communications, we measure the noise under the system, but we only take a 0.1 nanometer slice of that, which is 12.5 gigahertz. So OSNR is actually just the ratio of the measured noise to the noise, or sorry, the measured signal to the noise in this little slice. So the ratio looks like this. So you have this big, and it's the area under the curve. So you have this large, powerful signal and just a snippet of noise. Where if you do signal to noise, this measurement is you measure the power of the signal and you measure the power of the noise under the signal. So this ratio is going to be quite different from this one. So this is the idea. So for OSNR, if you have a narrow signal versus a wider signal, the OSNR is definitely going to be less for the smaller signal and wider signal. Even though your noise floor doesn't change, just the fact that your signal is getting bigger, it makes this number balloon. Whereas if you're measuring signal to noise ratio, it doesn't do that. And this is a cute little, slide here. I love math, it makes people cry. So I've got a physics major, I never like math. But anyway, here's the formula to convert if you want to go from signal to noise ratio to optical signal to noise ratio. And there's your slice of noise. Quality factor, this is what we measure in subsea. It's basically bit error ratio, but there's a transformation of it to what we call Q factor. It goes back a long ways. Here's the formula. If you ever have to deal with this, plug this into Excel and it will convert bit error ratio to Q. So hopefully that will help some people in the future. The old way of looking at signals, again, if this signal here is a 1 and it's a sinusoidal signal coming in, and this is a 0, they can drift in amplitude and they can drift in time. Q is basically, it's U1 minus U0. So U1 would be, say, your voltage level here to your voltage level for 0. So 0 may be 1 volt, this may be 10 volts. If this goes to 100 volts, your Q gets bigger, and your standard deviation is your variation. So your signal coming in, this is like a bunch of 1s and 0s coming in. There's 4 of them here. 1 came in high, 1 less, 1 lower, and 1 lower. So you're getting some deviation of this, and you can see over here, here's your standard deviation. So Q is basically your signal powers over your standard deviation. So what we do now in modern day optics, we don't look at 1s and 0s, we do phase modulation, and we put it on a grid called a constellation. So these are, instead of a 1 and a 0 being 2 points, this one has 4 points. It's quadrature phase shift keying for this particular one. Amplitude would be changes in this axis from your center. So this would be variations in amplitude, and this would be variations in time. And if you look at these constellations on a computer, this is what we simulated years ago when we first started doing this, and this is what was measured, very, very accurate. Each one of these tiny little points would be a 1 or a 0, a 0 or a 1 or a 2 with binary here. So again, this Q, it goes way back. This is the first time I was exposed to it back in '95. And AT&T Submarine Systems, we ran a system from them called an SL2000, and this is the Q measurement manual. Now this is done on the transponders. Q can vary in time, so we measure the variance of this time and the standard deviation. If you ever see TVSP, time varying system performance, all you have to do is get the standard deviation, multiply it by 5. So if this is 0.1, it would be 0.5, and that is your TVSP. And for submarine cable systems, you know, this may be what we do now, but we measure TVSP and we design and we assume that over the 25 years, it may go 5 times as bad. So this would be the ultimate worst case scenario you may see over 5 years. Geo scenario, I'll skip that. Here we are measuring, this is the Q on a submarine cable system. We turn the supervisory on, it drops hundreds of dBq. And then we turn the system off, it goes up a bit. So these are the signals here. Here's the spectrum. So we turn these on, turn them off. The lasers kind of are ugly. They look like this, but it is impairing the signal, but the amplitude here is so low that it doesn't make a difference, but you can see these measurements. So this is interesting what we're doing now with Bell Labs. It's sensing. So this is a submarine cable system that went from Virginia to France. And with this system, they're measuring vibrations in the cable. So if you look here on the American side, this is span number 3. So down here, you can see there's 12 hours of data here. It's fairly quiet. In the middle of the ocean, you can see here it's going crazy. This is geological activity here. And they actually measured the plates spreading. And over here, this is a span over here. Where's this one here? Way up here. This is the very last span, 75. And you can see there's a bit of noise, nothing, then a bit of noise here. So this could be, say, a vessel going over the cable or some activities going on in the area, maybe even be on shore. But anyway, that's what we're doing now. We can actually do this type of sensing in real time. I'll skip this. This is interesting though. This is a fiber, but within that glass fiber, like a hair, they've actually have 4 cores on it now. So this is one of the latest things that we're doing. We're doing optical meshes across the Atlantic Ocean. We're approaching the Shannon limit, so we're going as far as we can go with the data. And I think, yeah, this is interesting. Just a few years ago, we've only gone to 24 fiber pairs, so that's where we are now in the industry. And the last slide, if you get the slide deck, these are interesting things to see that I discussed. So I'll leave it there. How'd I do, Jason?
That was great. That was very interesting content. Really appreciate it. I did an Internet 101 session on our last one and kind of touched on subsea fiber a little bit, and I had a lot of interest right after that. And honestly, you were the first person I thought of, so really appreciate you getting on this and digging into this topic more. I mean, I think it's one of those things we all hear about but don't know much about. So great stuff.
A pleasure. Thanks for inviting me.
All right, so we're going to transition over to Mike Glaser. So Mike has been an engineer with Cox Communications for 25 years, specializing in power and grounding in critical facilities, commercial, customer premise, and outside plant applications, and the development of engineering and operational technical standards and procedures to ensure availability and reliability. He has been focusing lately on energy management, efficiency, and sustainability. So Mike, if you're ready, I just passed it over to you and you get started.
Okay, thanks a bunch. Just wanted to share my camera for a bit, which I think I did, but maybe I didn't. Anyway, we'll get right to it. I appreciate it, Jason. Thanks for asking. And we'll get into power in the head ends and hubs. So I have I had a stop at the top of the hour, but I actually can go a little longer. I postponed a meeting for 30 minutes if that's necessary, but I can still try and cover it up until 11 if that's all right.
Oh yeah, that's great. Well, we'll do a time check around that time and we'll see, but that should be no issue at all. Thanks.
Sounds great. All right. Okay. All right, so starting off, you put yourself in the position of a critical facilities or head end tech. You get a call from the network operations center, all kinds of circuit issues, no one's sure what's going on, bunch of chickens with heads cut off, so to speak. But you're pretty good at what you do. So you put 2 and 2 together and you realize that a bunch of stuff at whatever you want to put in there as a head end name has gone down. So the question is, as you're on your way there, what do you need to know? What are the questions that you're going to ask? There's no one else to call. You're on call. And what tools are you going to need? What scenarios are you going to go through in your mind on the way to the site? What'll be the sequence of your troubleshooting techniques? Well, that's the scenario setup. So we're going to take a look at a bit of an overview on power within the critical facilities. Head ends and hub sites is what we call them here in the cable MSO industry. Central offices, data centers, in telecom and in the data world, but they're all starting to look the same. I think a lot of us are realizing. But we're going to talk about trends in power, a little bit of Ohm's law, how the critical facilities power system works, all of the elements, backup and redundancy, polarity, grounding, alarms, monitoring, maintenance, and then types of rectifier plants that we have in the head ends and hub sites. So in the convergence of cable, data, telephony over the years, the infrastructure has changed. In the old school head ends and data centers, you had traditionally AC powered equipment. Now it's mostly DC powered. What was once thought of as luxury services, no longer true. 24/7 reliability is now a top priority, especially with wildfires after Katrina and all kinds of stuff like that. You know it as well as I do. No one's prepared to have their services go down any longer. A lot of the old sites had raised floor, and whether you're with Comcast, Charter, or any of the other MSOs, a lot of us have legacy sites that we have acquired, and so there's all sorts of mixtures of raised floor, hot aisle, cold aisle, maybe, different types of grounding from the different acquisitions that we all had. So there's pretty much a mixture. A lot of times there's a UPS backup anywhere from 10 minutes to an hour, and typically single generator. Now, that's how it used to be, and at least in Cox anyway, there was a change in the late 90s. We went more towards the telephone central office configuration, so almost all the equipment is DC powered, and there's a few peripherals that are on AC. We have the AC versus DC discussion on a regular basis, and I won't go into it here, but I'm happy to have that discussion with anyone who wants to spend some time, on another call. The telcos have used Neg 48 DC for a long time. It's negative because when the circuits were under the ground, the negative ionization would preserve the it fights corrosion in the cables, and 48 volts DC sort of sits nicely with 12 volt batteries. The thing about DC that is untrue about AC, of course, is that you can store it. So it has to do with the conversions, and every time you convert from AC to DC, you get some losses and some efficiency losses, and that's the deal. And if you really look at it, everything operates on DC. Your computers, once you're past the power supply, it's all 1.5, 12, 24, 5 volts DC within any of the equipment. So These days, a 4 to 8 hour battery backup is common, and at least in the Cox sites, dual generators is something that we have. And again, the critical 911, 911 services, you know, they can't go down. So increased power density is something that we have seen over the years. You know, we used to look at maybe 1 or 2 kilowatts per rack, but it's getting more towards 5 to 10 kilowatts per rack, depending on what's being done within the rack, whether there's a lot of cloud compute or things like that. So the things that are cool to know in terms of just handy little calculations is BTUs, basically. So if you take you know, your equipment within a rack and it's X number of watts, you multiply that by 3.412 and it gives you your BTUs, and it's which is basically heat. So when you design a critical facility in terms of how much cooling you're going to need, that's where you would you know, design a certain amount of tons of HVAC to what is the proposed heat load, and you would actually take a look at the floor space and calculate basically how many racks you could put in there, and assign a certain kW per rack based on what you have, what you know, and you know, and recent trends, and maybe a little bit of headroom, and then do the conversions, and then you would have the cooling that would be required for each of the rooms. Now, if you're having expansion capabilities, you would of course size your service entrance accordingly, or at least for the capabilities of being upsized. A lot of times with these days, modularity and flexibility is pretty much wherever we can go, so you don't have to go in and do a lot of construction work. You may want to have enough conduit sized properly so that you could pull larger conductors in if you need to, so that the you know, service entrance would be able to take the ultimate size of the building, and you have enough HVACs, you can expand you know, UPS modules, any of those types of things. 1 ton of HVAC is 12,000 BTUs. So Ohm's law, probably most folks on the call are familiar with it. And the you know, the deal basically is that if you know any 2 of those, you could calculate the third basically. So the way that we normally do it in a critical facility, and here's some examples. Let's start with a hair dryer. If it's a 1500 watt hair dryer and the nominal voltage is 120 volts, you basically take the watts divided by the volts, and that gives you the current, which is 12.5 amps at 120 volts AC. Now with a motor is the second calculation there. There's a power factor that's involved. Now that's also a single phase. If there was a 3-phase motor, it would be another calculation involved as well. The router nameplate, this is one that we can relate to. It's a 750 watt router, and the nominal voltage is 48 volts DC. So you take those watts, divide it by 48, and you have 15 amps for your current. So critical facility power systems, there's a lot of elements, and so we're going to talk a little bit about you know, how all of these things fit together. There's your AC input, which goes into your DC plant, also your generator backup, and there's grounding, monitoring, and alarms through all of the equipment. You have a UPS potentially, battery strings, and inverters, converters, 120 volts, maybe 24 volt equipment, 48 volt. You have your distribution panels, BDFBs, BDCBBs, and we'll talk about all those things, ultimately getting to the load equipment. So first of all, the AC power comes in, it's rectified, converted to DC power by the DC plant, which is a bunch of rectifiers. Now, what that DC power is used for is to power the load and then trickle charge the batteries. When the AC fails, the load is powered by the batteries alone. Over time, the battery voltage drops, and we typically engineer a 4-hour backup for sites with dual generators, 8-hour for a single generator. Now I should have changed that to 3 hours and 5 hours. We've changed that mainly because I think, as a lot of folks probably know, is that if you're on battery, your HVAC is not working. And so if you can get to even 2 hours without all of the equipment crapping out, you're lucky. So engineering for those extra hours isn't necessarily going to get you anything if the equipment temperature exceeds the threshold. Now, when the AC power returns, the load is powered again by the DC plant, and the batteries are back charged. The DC plant will be at full current capacity for a while until the battery voltage comes up. But the load out on the equipment room floor is always going to get what it wants. The batteries are just going to get whatever else is left over coming out of the plant. So what are the pieces of this power puzzle? How do these all fit together? We're going to go into that. So the way I like to break this up is normal elements, backup elements, and then miscellaneous elements. So the normal elements would be your utility AC power. You're going to have surge suppression. You're going to have transformers, typically rectifiers. You may have inverters, converters, which steps the DC up or down, and it may change the polarity. And then engineering examples will probably go into maybe just one of them, perhaps. So your utility AC power is coming in. There's a main knife switch behind that panel. 480 or 208 3-phase, depending on the size of the hub or head end. 120 or 240 for small hubs. And the NEC allows for more than one service. That's the National Electrical Code to a building if it's a certain size or there's increased capacity requirements. But the AHJ, the authority having jurisdiction, is always the last word on any of those types of things. So with surge suppression, you think of surge suppression at the critical facility level, at the AC electrical panel level, and of course, even at the circuit level, anywhere from gas tubes to metal oxide varistor technology to silicon avalanche diode. They all have their pluses and minuses in terms of how quickly they work to suppress the surge, and also whether they are killed instantly or you can actually use them over again. Transformers basically takes an AC voltage and steps it up or down. Typically, it's a step down in our critical facilities. And we have dry type. These are the ones that you see here in the picture. Liquid filled, those are usually for larger and industrial applications. And then K-factor rated transformers, they are basically, they have more windings and they're more robust. So that's something that when you are feeding rectifiers, it's a good idea to use those. They basically mitigate any harmonics and other losses. So rectifiers in a DC plant, they take an AC voltage, change it to DC. Inside of it, there's going to be rectifying elements, transformers, protection circuits, filters, voltage control, alarm circuits. And the old school was ferroresonant, silicon controlled, similar to the ferroresonant outside plant power supplies. Large components, heavy equipment. The power density is inefficient. The efficiency in and of itself is not great. Now, in the past 25 years, modular, or 30 years really, high frequency switch mode rectifiers have been used. They use smaller components. There's a higher power density. It's easier to maintain N+1 redundancy. So what happens within those is that it boosts up the frequency so you can use smaller components and as you probably have seen inside of your head ends, the rectifier modules are becoming smaller and smaller. Now here's some pictures of a few older ones. I could have updated them because they're even smaller than these days. So as you can see, they're generally plug and play, and you can have small customer premise size up at the top right, and you can have the larger head end size in the center, the upper center alpha plant, and everywhere in between. So some of the desirable features for modular rectifiers, you can remotely monitor them. They have temperature compensation and high voltage shutdown, adjustable current limit. So the rectifiers are pretty smart these days. The controllers are able to do an awful lot. They can manage the plant. They can, if you have sort of green considerations, they can cycle through the number of rectifiers that you have so that they're not all on at the same time. Only the number that are needed are on, and then the rest are in standby, and then you cycle through them to make sure that they all get a little bit of use. Well, that's all possible these days. So if you're looking at rectifiers, one thing that you want to do is you want to take N, which is the number that you actually need based on the load, and then add 20%, and that would be generally for battery recharge, and then a N+1. So for example, if you have a load of 1200 amps and you take 20% of that, which is 240 amps, this is all DC. You take that 1200 and add it, it's 1440. So if you're using 200 amp modules, you would then say, well, divide that 1440 by 200, we need 7.2. And obviously you're going to round up. So that's 8, and then you add 1 for redundancy, so that's 9. Inverters take DC power and convert it to AC power. And that's for equipment that is AC powered within the critical. There's a lot of folks that come into the critical facility, well, not the critical facility engineering necessarily, but the equipment owners, a lot of them come from the data center world, and they're used to everything being AC powered. The thing about now that we've converted all to DC, inverters are notoriously tricky. So we can't guarantee the same reliability when your equipment is on inverter as it is when it's on a 48 volt DC. That's just the way it is, because there is switching involved. And when there's switching involved, things can go wrong. So the inverters are similar to the rectifiers. They're basically, taking one type of voltage and converting it to the other. It's just the opposite way. And FYI, there are companies these days that make rectifiers and inverters. They might call them rectiverters or whatever, but basically these are power conversion equipment that can take AC or DC in and put AC or DC out, depending on what you need. So think about how interesting that is, where you could have an infrastructure where you could tell people who are putting equipment in there, it's like, yeah, you can go AC or DC, we don't care. And you just build the infrastructure to take a full AC or a full DC load, which, it's a little bit more expensive, but then the flexibility is there so that you don't have to worry about it in the future. Future-proofing, that's one of the things. Modularity, flexibility, and future-proofing is something that I think a lot of us are thinking of, not just in the power world, but we're really wherever we can in our networks. So here's some, pictures of modular inverters. Typically, they're going to have a disconnect switch, like a maintenance bypass switch, much as a UPS would. And really, a UPS is simply a big box which has a rectifier and an inverter and batteries in it. So it takes these elements that we're talking about and just chunks them all together. So the inverter maintenance bypass switch, you're going to have one of those so that in case you need to work on the inverter plant itself. Won't go into the inverter engineering example. In converters, basically, it's like the DC version of a transformer. So it takes a DC voltage and changes it to another. We had some positive 24 volt equipment for a while. QRAM amplifiers were running on 24 positive, if a lot of you folks can recall. And so we used to have a 24 volt plant separate from the negative 48 volt. But eventually we realized, the load is so small, let's just put some converters to take the 48, convert it to negative 20 or positive 24, and then power the QRAM amps that way. So that's basically what you can do there. And here's an example of DC to DC converters. So now we're going to talk about the backup elements. And these are going to be your batteries, generator, and then an automatic transfer switch or whatever switching is involved. And we may talk about some engineering examples. The two types of telecom batteries that we use are valve regulated lead acid, and they're either gel or AGM, which is absorbed glass mat. And for those of you who do your work or engineering in the outside plant, I mean, you know all about batteries as well. And gel had been used for a long time. AGM is more common these days. Now, in the critical facilities, we had, well, not at Cox, but a lot of the telcos did wet cells, also called flooded or not valve regulated, but vented lead acid. Those are the ones that, especially if you were in the military, you may know of these as well, or in utility switching stations, where that's the ones where you have to take the specific gravity, and they're in clear, square, typically large containers. And in about the mid 90s, we started using the valve regulated batteries, which are quote unquote maintenance free. And so the types there are, gel and AGM. Almost all batteries now are a combination of a gel and AGM or just pure AGM. It just depends on the application. Some are better for some things. And then in the newer technologies, and probably a lot of us are investigating things like lithium and other types of technologies. High temperature tolerance batteries are available now, thin plate, pure lead with micro catalysts and similar types of improvements to the lead acid batteries. Like I said, hybrid supercapacitors, lithium ion, nickel, zinc, various other technologies. Here's some examples of valve regulated lead acid batteries. On the left and on the bottom, you see, large, 1600 amp hour stacks. 2000 amp hour stacks are available these days. And each of those 2000 amp hours stacks will power probably about 500 amps of load for about 3 hours, let's say. And the smaller monoblock batteries in the upper right, you'll see those in outside plant, maybe business services cabinets, customer premise sites where you have DC plants and you need the battery backup there. A lot of us used to use the 8-hour backup at customer prems and cabinets, from the telecom world. So a sizing example, let's say you have a 2000 amp plant, you need 4 hours of battery reserve. The existing load is about 1400 amps. So you have to consider what's the max capacity that this DC plant can expand to, because then you're going to need that much battery space. The thing about batteries, of course, is you only buy as many as you need, and they have maybe a 10 to 15 year life depending on the type of battery. The larger ones are 10 to more like 15 years these days. So you need to have enough floor space so you can put as many batteries as you're going to need there for the ultimate size of the DC plant in the room. So you have to look at the low voltage cutoff of the equipment. And each of the equipment manufacturers is going to have a threshold. Usually it's from 36 to 60, but some of them, some of the equipment on the floor will cut out at like 42 volts. So let's say it's 43.12. You got to find it out for each site, of course. And then we have a 2-volt drop. So think about this, is that from the battery terminals to the end of the line equipment in the racks, basically there's a lot of copper involved. And so whenever you have copper, you're going to have I squared R, that's current squared times resistance losses, which is again Ohm's law. But that's why high voltage lines have the voltage so high, so that they can go long distances. But for these DC cables, I mean, it's an AC in the AC world as well. But for the DC world, we engineer for a 2-volt drop from the battery terminals to the end of the line. So that means we have to have 45.12 at the battery terminals. And if there's 24 cells in a 48-volt string, then that equals 1.88 N volts per cell. Now, why do we care what the N volts per cell is? We're gonna see that in a second. So based on a chart that you're going to look at, you're going to say that for 1400 amps, 5 battery strings are going to be required. And we'll look at the chart later on sizing the batteries, but manufacturers have charts where you can go to a certain N volts per cell, depending on what you need to, and a certain number of hours of backup, and you just look at the chart and pick the number. So we talked a little bit about UPSs. They have alarms, they have a maintenance bypass switch, typically a screen which will show the the load, and typically the telemetry you can get into. And with these batteries, and these are more like the Group 31 size or similar, like power supply batteries, car batteries, etc. They're not like telecom batteries. Telecom batteries are slow rate batteries. These are high rate batteries typically, because you're going to have a UPS that's going to, maybe 10, 15 minutes, typically maybe a half an hour. So they're used to taking a high load very quickly. So they're basically, think of it as a sprint, or being pummeled in a boxing ring. That's what happens with these batteries, and that's why their lifetime isn't that long. Maybe 2, 4, 5 years. They're just a different application, different design. But and they have thinner plates. They're called high rate batteries. The telecom batteries that are there for like 3, 4, 8 hours, those have thicker plates, and they're used to more like of a long, slow distance run type of a thing. It's just a different application. So the chemistry and the composition of the batteries are a little bit different. Now, generators, you're going to have backup for your generators. All large sites have dual generators in the Cox network. Others are soon to be dual. We pretty much started to do that whenever we had telephony. We wanted to make sure that we were able to have redundancy. Now, if we don't have a dual gen set for maybe some of the smaller sites, we certainly would have a hookup for a portable gen set. And each of our markets would have a portable gen set that they could take to on a trailer to any of the sites that needs it. So you want to make sure you have large enough tanks to get you through, say, a long weekend. In some of the hurricane areas, we recently upsized the tanks. If you have good relationships with your local diesel vendors, you may be able to get priority. Of course, the hospitals and other lifeline systems are going to be getting top priority. But we try to control what we can. So when you're doing the generator systems, you want to make sure that you're going to choose a certain fuel. And there's multiple fuel generators these days. There's linear generators, which are a whole nother type of interesting technology. And you're going to look at the applicable codes, the distance of the tank from the buildings, property line, where are you going to locate your ancillary equipment, your transfer switches. You're going to make sure that you can have them outside or inside. Monitoring panels, concrete pad. What's the voltage selection? You're going to want to stub up conduit up ahead of time. To make sure that you can run all the alarms and the controls. So here's a couple of automatic transfer switches. PLCs are another sort of version, programmable logic controllers. They're basically breakers that act as transfer switches. Now we're going to talk about distribution elements. So the power is generated by the DC plant or the inverters or the UPS. The batteries and the generators are the backup. And then the distribution elements, these are the things that take the power to the equipment. So we're going to talk about cable, bus bar, lugs, shunts, circuit breakers, fuses, fuse panels and circuit breakers, BDFBs. If you're not familiar with that, that's an old telecom term meaning battery distribution fuse bay. And used to be they were all fuses, but nowadays most of them are circuit breakers. So we say BDCBBs or battery distribution circuit breaker bays, but that's a mouthful. So they're still called BDFBs just because. And we may go into an engineering example or two. So the cable within a critical facility, you have to make sure that, it's VO rated, in terms of fire suppression and all that, low smoke flame. THHN is generally frowned upon, at least for the large cable. And that's THHN is your standard, AC power cable. So RHW or RHW2, you may have seen them. They're sort of, typically they may have like a cotton braid, green for ground, red for battery, black for return. They may be stranded or flexible. Now this, red for battery, black for return. A lot of folks, I'm just going to have this conversation just in a couple of minutes. People confuse whether red is positive or red is negative. And here's the way to think about it. Now, not all the manufacturers know this because they still think that everybody thinks that red is positive and that's just the way it is. Well, that's because everyone's used to the automotive industry where you have a negative ground in your vehicles. But when you have negative 48 volts, you have a positive ground. So the negative is red and the positive is black. So the way to think about it is that the way it should be is the red should always be hot, whether it's negative or positive, and the black should always be the return or the neutral or the at ground potential, let's say, right? But again, not all the manufacturers do that. You'll get equipment that has these colors, and so don't go by the colors. Just use your meter. That's the moral of the story. Okay, now on the cable sizing, basically, you're going to look at what's the ampacity, and then you're going to use this table from the National Electrical Code. So, for example, if you have, let's say, and we would typically use the 90 degree, but let's go ahead and with the 75 degree. So if you have a 65 amp load and you got to size it to the breaker ultimately, then a number 6 cable is the size you're going to use. And if you have, say, 200 amps, you're going to use a 3/0, or really probably a 4/0 because 3/0 is not too common. Bus bar is what the cable is going to be connected to. And these are large copper bars that you'll see throughout the critical facility power room, the main DC plant bus bars, battery termination bars. They got to be rated for the amp load, just like a cable would be. Typically a 1/4 inch thick, 3/8 inch holes, lugs. Burndy, T&B, ILSCO, Panduit. You have your larger ones, you have your smaller ones that go to the equipment. You have narrow tongue, insulated, ring, spade, 1 or 2 hole, Always want to order spares. You want to order them with an inspection window and clear heat shrink if possible. That's how we are able to see if you are actually crimping them properly. Now, what a shunt is basically a fusible link. So that's used for measuring the amount of current, typically, that's going through a DC plant. Now, circuit breakers, I think we all know what those are. And you can see them in the fuse panels, you can see them in the BDFBs, you can see them in the main plant. You also want to keep spares of those. Battery disconnect breakers are another form of a breaker, of a disconnect. So every battery string typically has a disconnect. Some of the telcos used to not do that. I think most of them do now, not all of them, but they didn't want to have any single points of failure. But you want to make sure that the battery disconnect is sized properly so that it could take the full load of amps that are going out of that battery or into it in recharge. Here's some GMT fuses. I think most of us have seen those. They're fast acting, different colors for the different ampacities. Here's a couple of examples of fuse panels and breaker panels that are inside of the critical facility or at the top of the rack or cabinet. And typically these are going to have an A and a B feed. Almost all equipment has redundant power supplies, redundant feeds. And here's some pictures of some BDFBs. More pictures. And as you can see, the way that it's done with the lacing of the cables, the P tags and labeling and everything, when it's done properly to the telco standards, it really is a beautiful looking installation. But that's an art that's dying out, the 9-ply twine and all that. Then the Telcordia, Ericsson, Bellcore, GR 1275 is the standard that talks about how to do all that stitching, the Chicago stitch, the Kansas City stitch, and all that kind of stuff. They got pictures and all that. But actually, us telecom and MSO companies, if you're familiar with the Motorola R56, that's really the Bible for engineering and planning, designing, and operating a critical facility. If anyone has questions or needs contact info or resources afterwards, please let Jason know, and we can make sure that we get hooked up with that. Also happy to have a chat with folks, at any time on any of these things. So the miscellaneous elements that are frequently overlooked but just as important. We have grounding, alarms, monitoring, environmentals, cable management, and the low voltage disconnect if you have one. So we're putting this all together, and now you should be able to look at this drawing and have a pretty good idea about what's going on here. The AC power comes in, it may come from the generator if the utility power is gone, but it goes into the DC plant, and there's battery strings involved. There's a UPS and battery string potentially, which then powers the AC equipment. The AC equipment can also be powered from an inverter that's hanging off of the DC plant. The distribution fuse panels, breaker panels are upstream of the equipment. You may have a converter for 24 volt or other voltages, and then your neg 48 with the other miscellaneous elements, grounding, monitoring, etc., involved. So we want to have a backup and redundancy mindset. A and B feeds. Now, sometimes they're not redundant, but they should be. You want true load sharing if you can, N+1 redundancy. You want the stuff never to go down. And also you want any changes, maintenance, grooms, adds, whatever, as well as any powers to be transparent to the customer. And for power engineers and power critical facilities techs and all that kind of thing, a lot of times it's sort of like, a lot of folks don't understand all that goes into it. I mean, when we're talking about HVAC and fire suppression and all that other stuff, it's a lot of stuff that goes into it. And so it's like, you know, people only notice it when you know, things go wrong. But when things go right, everything's running smoothly. You know, it's pretty much a behind the scenes type of deal. With the polarity, colors are important, and they're also not important. And I talked a little bit about the automotive mindset, and the moral of the story is always use your meter before making any connection. Now with the grounding, some companies use what's called a PANI configuration on a master ground bar. So all the equipment is grounded, the racks, the frames of the chassis equipments, etc. And you try to have it all go to a master ground bar typically. And if you can, some companies don't do this, but if you could arrange the surge producers, absorbers, non-isolated and isolated on that ground bar, then that's what you need to do. It's mainly for administrative purposes. It's not like the lightning is going to, you know, or the surge is going to ask what direction it's going. It's just it's helpful for proper grounding methodology. And here's some pictures of some ground bars in the various rooms, some isolated grounds, etc. For the alarms and monitoring, I think most of us, you know about all that. It's very important. You know, you want to have some standardized maintenance program, and you know, all of the elements get maintained. And just a picture of a few of the different rectifier plants. Again, these pictures are a number of years old. Bottom line is that, you know, they look pretty similar, but they're smaller modules these days. So the power is taken for granted. It's always there, and we kind of like it that way. Hot work in the maintenance window, typically insulated tools, 2 people for safety. Always think about redundancy. We want the stuff never to go down, and we want to engineer for a worst case scenario, depending on the cost, but we also apply common sense and experience. So again, the scenario, you get the call from the NOC, all kinds of issues, the head end has gone down. What details do you know? Who to call? No one around, you're it. So what tools are you going to need? What scenarios are you going to go through? You know, what are the gazintas and the gazoutas of all these different elements within the critical facility? You know, troubleshooting 101, right? So here's some resources. Telcordia 1275, as I mentioned, the NEBS Telcordia GR63 is pretty good. There's a bunch of Cox standards that are on there, but the main ones are the ones that are listed there. The 1188 IEEE is one of the ones for batteries, valve regulated, and there's some ANSI documentation as well. And again, the Motorola R56 is another one. I didn't put it on there, but I can let you all know if needs be how to get a hold of that. Well, that's the presentation. I don't have anything else, so if there's time for questions, Jason, I'll leave that up to you. But I'm ready to roll along. And I put out that other meeting by half an hour, so I do have time.
All right, thanks, Mike. Great content. I mean, I don't know a lot about power other than it scares me. I mean, I think it's one of those things you need to respect it and follow proper procedures, obviously. If anyone has any questions, you know, feel free to come off mute or throw them in the chat. But I do have one question for you, Mike.
Sure.
As you know, as technology is changing and, you know, all the MSOs are deploying BCMTS and we're starting to do more and more server installs. So obviously almost all of our head ends are DC power. You know, traditionally we've always done DC power, but when you start doing a lot of racks full of servers, I mean, I think you could argue AC is a better way to go. What are your thoughts around that change or what that future head end might start to look like over the next 10 years?
Yeah, that's a great question. So the AC versus DC argument, there's a you know, and I have no dog in the fight, but you know, with AC, the ubiquity of AC and the ability of you know, folks who know how to work on it and all that kind of thing, that's a very strong argument. Although a lot of the Googles and a lot of the larger you know, hyperscale data centers are going DC because of the efficiency. and the fact that it's backed up, and the fact that there's no switching necessary. So I think that the ability to do AC and DC is pretty important. When we're talking about racks full of servers, you know, we've seen some of them that if they're not manufactured, you know, DC power supplies generally cost more. They may have a longer lead time as well. If we're talking pizza box servers, you know, it may be better to do them via, you know, AC. If you have redundant servers, you know, as opposed to redundant A and B feeds, you know, there's a few different ways to do it. And at the end of the day, it kind of doesn't matter to me. I mean, there's even been movements, and some of the folks in Asia have been utilizing 380 volts DC, and so that way you can have smaller cables. You know, so there's a lot of different ways to do it. I think the thing I mentioned about the equipment that could be AC or DC in or out is a pretty interesting thing, because then you just would build for an AC or DC configuration, and then you would utilize you know, whatever makes sense. But if the other thing too is if the servers are very power dense, then you're going to have potentially hotspots. So I think that it might make sense if you know that you're going to have a certain section of a room that's going to be you know, server dense, you may want to say, let's like put together like a pod with some close coupled cooling, maybe some in-row cooling, where you have containment. You know, certainly blanking plates and containment help, and then you may have, you know, distributed AC for that particular pod. And then, you know, the thing about that is that it scales real well. So there's a lot of folks that are doing their facilities with, you know, pod containers, if you will, you know, inside of a large, you know, hangar. So there's a lot of ways to skin the cat, and it really does depend on what is your, you know, what you're going to be doing, and you want to make sure that you have flexibility, future-proof built into it, and all that. You know, the question also comes up is like, well, power's moving out to the, you know, to the last mile and out to the field. So are we going to need as much? What are the head ends going to be looking like? And I think a lot of us are saying that, you know, we're going to have smaller facilities and maybe large cabinets out there, and then less of the large facilities, but larger facilities. So like what we were calling a broadband service center, in terms of a, you know, instead of a head end. And then instead of hub sites, you know, we have smaller, almost container sized, you know, 5 or 10 rack facilities that may be out there, and then some cabinets. But it's kind of hard to say. Hopefully I answered that a little bit without too much confusion.
Oh yeah, that was great, thanks. And we did have one question come in. Why 54 volt with 48 volt battery system?
Yeah, that's a great question. So the batteries nominal voltage is 48, but we float them at 54 because that is going to trickle charge them. It's going to keep them charged. And it also accounts, you know, for a 2 volt drop. Now that's for the valve regulated lead acid batteries. If we had the flooded or vented one, those like to float at like 52.5. So it really has to do with the specific gravity of the battery and the composition of the battery. So to make sure that there is a small trickle charge going into them. And then of course, when the power is out, you know, that 54 is no longer there. So they're going to go to sort of an open circuit voltage, which typically for these VRLA batteries would be like 51 maybe. They're going to go like right to there. There's a coup de froid, which happens where it might go down to, you know, 49 or 50 and then back up to, you know, 52 and then slowly degrade from there. But that's the reason, is so that the specific gravity of the battery's construction, and then to make sure that they're always with just a little bit of charge to keep them, you know, topped up and ready.
All right, thanks.
One other thing to mention to that is that when I mentioned about temperature compensation, typically most of the power rooms should be, you know, climate controlled. But if you do have hotter or colder than 77F, which is what batteries like, the valve regulated ones anyway, if you have hotter or colder than that, you may want to adjust the float voltage of the plant. You would want to adjust the voltage down a little bit to maybe 53. And if it's colder, you want to adjust it up above 54. But whatever the battery manufacturer requires at 77 Fahrenheit, that's what you need. And that's what's going to keep the batteries lasting long. Any other questions?
I don't see any other questions at the moment, but I just want to thank you, Mike. That was great content. I really enjoyed that presentation.
Thanks. It's been my pleasure, and I appreciate you, Jason, for asking me. Yep. And how do we get my contact info to the folks? So if they have any questions or or anything in the future, I'm always happy to participate, help out, and just have conversations.
Cool. Yeah, we'll either send a follow-up email out or maybe in our next newsletter, but we'll definitely get your information out.
Sounds great.
All right.
All right.
Thanks, Mike. All right, James, you ready to go?
Yes, sir. I am ready to go.
All right, cool. I'll introduce James real quick. So James Patterson with Calix is going to do a PON overview. So James began working with PON Technologies in 2008 when he joined WOW Internet Cable Phone as a member of the Access Engineering team. After 12 years with WOW, he accepted a position at Calix, where he worked as the resident engineer supporting Cox Communications for 3 years before moving into his current role as the Calix senior sales engineer for the Cox account. And actually, James, before you get started up, I've always wondered, is it Calix or Calix?
It's interchangeable. A lot of people call it Calix, but internally we refer to it as Calix. We answer to both.
All right. All right, thanks. All right, take it away, James.
Okay, are you guys able to see my presentation?
See PowerPoint. Yep, you're good.
Okay, outstanding. Let me get this guy out of the way. All right, good morning, everyone. As Jason said, my name is James Patterson, and I'm a senior sales engineer with Calix. And today, I'm going to be providing a high-level overview of PON networks. We're going to talk about what PON networks are, the components that make up a PON network, and some of the considerations that you have to be aware of whenever designing a PON network. So I'm happy for this to be an interactive session. If there's any questions along the way, please feel free to jump in, interrupt me, and I'll stop so that we can cover those questions as we move through the presentation. Okay, so what is a PON network? Well, PON stands for Passive Optical Network. And what it is it's a fiber optic point to multi-access point network that we use to deliver broadband services to subscribers. So everyone has heard of the term FTTH, fiber to the home. That's exactly what PON networks were designed to do, to deliver fiber to the home for subscribers. PON networks can cover distances up to 60 kilometers, depending on some considerations that we're going to learn about a little later in this presentation. PON networks consist of a group of common components that you're always going to see. There's always going to be an OLT. The OLT is the subscriber or the service provider endpoint in the network. There's always going to be ONTs in a PON network, and these are the subscriber endpoints that are installed at the customer homes and premises. And then, of course, there's always going to be the fiber plant and the optical splitters that we're using to connect all these devices together. So over the course of the next several slides, I'm going to dive into each of these, and we're going to talk about what they are and what they do and how they fit into the network. So let's start with the OLT. OLT stands for Optical Line Terminal. And as I mentioned before, this is the service provider endpoint in a PON network. So the job of the OLT is to aggregate the subscriber traffic and forward it to the network core. This is also where all of the subscriber provisioning happens in the network. So all of those broadband services that we're providing to our customers, like voice, video, data, internet services, those are all provisioned here on the OLT. as well as the bandwidth, the speed tiers for each of those services. So every OLT is equipped with PON interfaces and Ethernet interfaces. So the PON interfaces are subscriber facing, and these are used to terminate the ONTs that are installed in the field at our customer premises. So each PON interface of an OLT is capable of terminating upwards of 128 ONTs, at least in the case of XGS PON. But 32 and 64 ONTs per PON interface they're the more common deployment practices that we see today. The Ethernet interfaces on the OLTs are used to uplink the OLT to the upstream subscriber network, giving us the ability to deliver all of those services downstream to our provider or to our subscribers. These Ethernet interfaces, they can range in speeds from 1 gig all the way up to 100 gig. And more often than not, you'll see support for lag or port channels, giving service providers the ability to bundle these links together and provide more bandwidth and in some cases even some redundancy from upstream fiber cuts. The number of Ethernet and PON interfaces are going to vary depending on the model or the hardware that's being used for the OLT. OLTs, different models are available to provide a multiple different deployment options. Some OLTs are actually remote hardened nodes, environmentally hardened, that are designed to be installed in the field. These type of OLTs can be strand mounted. They can be installed directly on the utility pole. They can be placed in ground pedestals or dog houses like this one here. And then other OLTs are temperature hardened, making them ideal for outdoor cabinet deployments. And then, of course, central office data centers and head ends. These are all very common OLT deployment scenarios as well. So there's some benefits to deploying remote OLTs or cabinet OLTs, right? As I mentioned previously, that a PON network can cover distances up to 60 kilometers. So that 60 kilometers is the distance from the OLT to the ONTs. So the further that you can place your OLT into your network, the deeper the network penetration you're going to have, and you're going to be able to pick up some customers that you wouldn't necessarily be able to pick up that are closer to your head ends or your COs. So the next component we're going to discuss in the PON network is the ONT, or the optical network terminal. Sometimes you'll hear these devices referred to as ONU, optical network unit. These are interchangeable terms. They're the exact same device. They perform the same functionality, and they're the subscriber endpoints that are installed at our customer premises, delivering the broadband services to the customers. So whenever, by way of comparison, as we're going through this presentation, anytime you hear me refer to an ONT, compared to a DOCSIS network, it performs the exact same functionality as a cable modem. So whenever you hear ONT, just think cable modem. So ONTs come in various models as well, giving service providers the ability to deploy in just about any type of use case. They come in outdoor variants that are temperature hardened, and those are typically installed in outdoor enclosures, a lot like this one here. They come in indoor models. They can be wall mounted, set on the table. They can sit on a shelf. There are rack mount versions that are more ideal for more like multi-dwelling units. And then there are other ONTs that actually have the built-in functionality of a residential gateway, allowing a service provider to deliver managed Wi-Fi for their customers as well. The different ONT variants can also come with different interface layouts and different interface options as well. So you could have an ONT with a single Ethernet interface and one POTS interface for voice, all the way up to that rack mount ONT that we discussed earlier that could have maybe 8 Ethernet interfaces and 8 POTS interfaces. So there are a lot of different options when we're discussing ONTs. Okay, let's talk about the fiber plant and the fiber that we use to tie our ONTs and our OLTs together. So as many of you probably know, there's 2 types of fiber optics, right? There's multi-mode and there's single mode. Multi-mode fiber is used for short distance applications like router to router connections or router to switch. the type of connections you would see inside of a data center or inside of a central office. But when we're talking about PON networks, we're always going to be referring to single mode fiber for long haul applications. So if you look at the diagram here on the left, you'll see that our fiber has 4 layers. So starting with the innermost layer, number 1, this is the core, and it's the transmission medium for the fiber. And the core can be made of either glass or plastics. And the way that fiber optic communications between the OLT and the ONTs are accomplished are by sending digital signals that have been encoded into analog pulses of light into that core. And then at each end of the fiber, the optical receivers receive those pulses of light and convert them back into digital 1s and 0s. The next layer that surrounds the core is known as the cladding. And this is a reflective layer that is responsible for ensuring that that light that's transmitted through the core remains inside the core. So if we take a look at this cross section of a fiber cable to the right, we have the core in the center with the cladding on each side. And you can see that as the light is transmitted into the core, it bounces all the way down the length of the fiber. That's because it's bouncing off of the reflective walls of that cladding. So the core and the cladding work hand in hand to ensure that your light gets transmitted all the way down the fiber. Outside the cladding, we have a buffer, sometimes referred to as a coating, and this protects the fiber from mechanical issues. And then the outer layer is the jacket, and it protects the entire cable assembly from moisture, chemicals, and abrasion and other external factors of that kind. So most fiber optic applications that you see typically use a pair of fibers, right? You have one fiber for transmit and one fiber for receive. But PON's a little different. PON networks communicate bidirectionally. And what that means is that they communicate between the OLT and the ONT. All this communication occurs utilizing a single strand of fiber. And this bidirectional communication is accomplished by utilizing wavelengths. One wavelength for transmit and another wavelength for receive. And these wavelengths, they represent different channels of light. So this diagram illustrates this concept using XGS PON wavelengths. So the OLT transmits downstream to the ONT at 1577 nanometers. The ONT receives that light level at 1577 and transmits back upstream at 1270 nanometers, all over one strand of fiber. So something to point out, these wavelength plans, they're going to differ depending on the type of PON technology. Like I just said, this is XGS PON. What determines the PON type is the optic that's inserted here at the OLT. And then, of course, you have to have a corresponding ONT in the field to communicate with it. So if we had XGS here, this has to be an XGS compatible ONT. We're going to get deeper into these wavelength plans and technologies a little later on in this presentation. Okay, so as I mentioned previously, each OLT PON interface can terminate upwards of 128 ONTs. And the way that we do this is by utilizing optical splitters. So optical splitters take the light that's transmitted from an OLT PON interface, and it evenly splits that light across a determined number of outputs, to which each of these outputs can then be connected to an ONT in the field. So this block diagram here at the left, as you can see, the PON interface connects to a 1/16 splitter. So what this means, the 1 tells us the number of inputs that this splitter can accept. And then the 16 tells us the number of outputs. And then on the right, we have the exact same thing. It's just a 1/32, illustrating that we can connect up to 32 customers off of this. So optical splitters can be installed in COs, head ends, remote cabinets. They can even be placed in outside plant splice enclosures. So while it's possible to take a PON interface and run it into a single 1/32 or maybe even a 1/64 and connect your ONTs that way, the more common method of arriving at the split ratio you're looking for is by a process called cascading. And what cascading means is just simply to place multiple optical splitters in series. And there's a lot of different ways of doing this, but this example shows a very basic method of achieving a 1:32 cascaded split ratio. So here we're taking the PON interface from the OLT and we're taking it into a 1:4 optical splitter. It's split 4 ways, and each of our 4 outputs are then fed to 1:8 splitters, giving us the ability to connect up to 32 ONTs off of this single PON interface. So if we wanted to double the capacity, say we wanted to do a 1:64, we would just go through here and replace each of these 1:8s with 1:16s, and we would get to a 64-way split. But as we're going to learn in the next section, there's some factors that we have to take into account when we're designing PON networks before we just willy-nilly go through and start replacing optics with our optical splitters with higher split ratios. Okay, so just a real quick summary of what we have so far and what we've covered. The service provider, the OLT, is going to have multiple PON interfaces that are going to connect to our plant fiber, which is going to include our optical splitters in the field, and those are going to connect to our ONTs. And then on the service provider side, we have our Ethernet interfaces connecting the OLT to the other, allowing us to deliver services to our customers in the field. Any questions on any of this so far before we go into the next section? Okay. So when we design PON networks, we have to understand that how that fiber plant is going to affect the light that's being transmitted between the OLT and the ONT. We have to understand what's going on there so that we can design our plant in a manner that these devices are going to communicate successfully, and we're not going to run into any issues. And the 2 biggest factors that we have to be aware of are optical power and dispersion. So what is optical power? Well, optical power is basically just the intensity or the brightness of the light that's being transmitted into the core of the fiber. And as that light travels through the fiber, the intensity of the light diminishes as it becomes absorbed by those glass particles and microscopic imperfections in the core. And this loss of intensity is what we call attenuation, and it's measured in decibels. So when we talk about decibels, we're not talking about a unit that expresses a physical measurement in and of itself. A decibel is a dimensionless unit that's used to express the relationship between 2 values. So what it really is a ratio. So to explain what a decibel represents, a 0 decibel would indicate no change, +3 decibels would indicate double, and -3 decibels would indicate half the signal. So to express an absolute value like light level, the decibel has to be compared to a known reference value. And in optical networks, that known value is 1 milliwatt of power. It's expressed in dBms. So if we take a look at what this means when we're comparing optical power in dBms, as we discussed, 0 indicates no change. So in dBms, this is equivalent to 1 milliwatt of power. +3 indicates a doubling of the signal, so that indicates 2 milliwatts of power. And then -3 represents half, so in dBms, that indicates that we're at a 0.5 milliwatt of power. So it's crucial for us to understand the expected amount of attenuation that we're going to see in our networks when we're designing them, because the OLT optics, the PON optics, and the optics that are built into each of the ONTs in the field, they're all rated and they all have a specified minimum and maximum operational value. So if the optical power that's being received is either too high or too low, the OLT and the ONT, they're not going to communicate with one another. So this little block diagram here shows that this ONT has a receive level, a receive rating on the high side of -9 dBm, and on the low side, -28 dBm. So while our OLT over here is transmitting at about +3 dBm, we have to ensure when we build out our plant that we've included enough attenuation in our design that the light level, by the time it reaches this ONT, it's going to fall somewhere between -9 and -28 dBms, allowing this ONT to come up and communicate. So what are some other factors that contribute to attenuation that we need to be aware of? So in the previous slide, we talked about how glass absorbs light as it travels through the core of the fiber. So the longer the distance, the more fiber length that you have, the more attenuation you're going to introduce into the PON network. So fiber length and distance is one of the biggest factors that contributes to attenuation. Optical splitters. So obviously optical splitters by their very nature are going to inject attenuation, right? We're taking an input from a PON optic off of an OLT and then dividing it, upwards of 64 or even 128 ways. So this is going to cut our light level drastically. Splices are also a factor. Each splice introduces a small amount of attenuation into a PON network. Not much, but a lot of splices do add up. Connectors. So connectorized fiber jumpers are patch cables used to, like the ones that are used to connect the ONTs at the customer premises. Each connector injects a small amount of attenuation that you also need to account for. And the same can be said about any connectorized jumpers that are used in head ends or patch panels or FDXs to extend the PON network. Any bends that might be in a fiber jumper. Sometimes you'll go into a head end or to a CO and you'll see a connector that maybe the guy that ran that jumper, it wasn't quite long enough, and you'll see it stretched out and have a real sharp bend on each end. That is definitely going to cause some attenuation and possibly some performance issues. Dirty connectors. So anytime any of these connectorized fiber jumpers are used, they really should be visibly inspected with a scope and cleaned if necessary. I can tell you from experience, a dirty fiber is going to introduce all kinds of problems and frustrations, and you're going to have a whole lot of fun and hours figuring out why your ONT or even ONTs are bouncing and not necessarily working correctly. So before any fiber jumper is installed, it should always be scoped and cleaned. And then the final thing that I'm listing here that can cause attenuation are optical pads. And these are just small devices that are used to intentionally introduce attenuation into a network, typically to reduce optical power to an acceptable threshold. You don't see them very often in production deployments, but they are pretty useful in lab settings. So the biggest takeaway that you need to know about attenuation is that attenuation is ultimately going to limit the distance that ONTs can be placed from the OLT. So earlier when I mentioned that PON networks can cover distances up to 60 kilometers, well, that OLT PON optic, it might be rated for 60 kilometers. But if you design the network where you're taking that 60 kilometer optic and you're splitting it 64 or even 128 different directions, right? You're really going to limit that distance. It's going to come down from 60 kilometers. So that has to be taken into account when building out the plan. Okay, dispersion. So for the purposes of this overview, I'm not going to get too deep into the weeds when it comes to dispersion, but I do want to give a high-level overview so that you have a little bit of an understanding as far as what it is and how it's going to affect a PON network. So dispersion basically just means to spread out over time and distance. So all power disperses, sound waves, electrical signals, light waves. Think about dropping a pebble into a perfectly still pond. As that pebble enters the water, the resulting waves near that point of entry are going to be very distinct and closer together. But as those waves start to propagate further away from where the pebble entered that water, they're going to start to spread out. They're going to become less pronounced and distorted. And so this is dispersion. And this concept, it also exists in optical networks. And the result is signal degradation. So dispersion in PON networks, it's the result of a couple of different factors. The first of which is that light frequencies propagate at different speeds through material, slowing and bending as they do. So this is pretty much how a prism works, right? So in our case with PON networks, that medium that the light's propagating through is the glass or the plastic fiber core. These variations in speed cause the signal to become distorted or smeared, and to the point that at the end, the optical receiver is unable to recognize that signal. Another cause of dispersion is imperfections in the shape of the core, which affects how light travels through the fiber. So the core is not perfectly round, so this can slow the light waves down as they travel through. So there's different types of dispersion. Again, I'm not going to get too deep in the weeds on this one. The biggest takeaway here is that as those light waves travel through the fiber, they begin to spread out, becoming distorted and unrecognizable to the far end receiver, which is then in turn going to cause bit errors and impact performance and network capacity. And because of this phenomenon, like attenuation, this also affects the maximum distance that an ONT can be placed from the OLT. So here we have a visual representation of a light wave as it travels through a fiber, bouncing through the core all the way through the far end where it exits. So you'll notice here that the glass is absorbing that light as it passes through. So if we were to extend this tube, we would notice that as the light travels further away from the light source and gets farther away, it's going to start to become more dim as attenuation takes its toll on the signal. And also, as this light wave travels through, you would notice that the distance between the crest here would also start to change, as dispersion would also take its effect on the light signal. Any questions on either of those concepts before we move on to the next section? Okay. So PON networks have evolved over the years, each new technology providing additional bandwidth available and service delivery options. So in the next section, we're going to cover the prevalent PON technologies that you're most likely to see today. And we're going to start with EPON. So EPON, or Ethernet PON, as the name implies, this is an Ethernet-based PON technology. EPON is symmetrical, meaning that each PON interface delivers the same amount of bandwidth in both directions, the downstream and the upstream directions. The EPON interface provides 1 gigabit in the downstream and 1 gigabit in the upstream direction. And then this bandwidth is shared for all of the ONTs that are connected to that interface downstream. And as we discussed earlier, we talked about how OLTs and ONTs communicate in a bidirectional manner utilizing wavelengths. You can see here that EPON uses a wavelength plan of 1490 and 1310. So the OLT is transmitting downstream to the ONTs at 1490 nanometers. These EPON ONTs receive at 1490 and transmit back to the OLT at 1310. And as you can see, this is all done over one individual strand of fiber. The next PON technology we're going to talk about is GPON. GPON stands for Gigabit PON, and this one's been around since about 2007. This is an asymmetrical PON, meaning that it provides more bandwidth in the downstream direction than it does in the upstream direction. So as you can see here, GPON provides 2.4 gigabits downstream and 1.2 gigabits in the upstream direction. And because this technology offers more than double what EPON does, you can see here why GPON has become a popular choice among service providers over the years. There's a lot of this that you're going to see in the field. Something else you'll also notice is that the wavelength plan is the same as EPON. It's using 1490 by 1310. 1490 from the OLT out to the ONTs, and then the ONTs transmit back upstream at 1310. So those two technologies have been around for a little while, but as the connected needs of our subscribers have evolved and people at home are streaming Ultra HD video, they're doing more gaming, there's home security applications with cameras, folks who are working from home. All of these things have pushed bandwidth requirements higher and higher and have contributed to bandwidth saturation on some of these EPON and GPON networks. So this is where XGS has really come into its own. XGS-PON is a higher bandwidth symmetric version of GPON, and it offers 10 gigabits in the downstream direction and 10 gigabits in the upstream direction. So real quick, let's get out our secret decoder ring here and interpret XGS, right? So the X here represents the Roman numeral 10, G stands for gigabit, and S stands for symmetric. So that's what that means, 10 gig symmetric PON. And one other thing you'll want to note here is that XGS-PON deviates from the wavelength plan that's shared by EPON and GPON, the 1490-1310. XGS-PON uses 1577 in the downstream direction towards the ONTs, and then the ONTs transmit back upstream at 1270. So this difference in wavelengths makes XGS-PON an ideal technology for a service provider who's looking to migrate from EPON or GPON, because it permits us to do something with both technologies by putting them on the same fiber plant, doing an overlay network by utilizing a device known as a coexistence element. And what a coexistence element is it's a device that combines two PON networks of differing wavelengths and allows you to connect them onto a common fiber plant. So this simple block diagram offers an illustration of this concept. Here you can see we're connecting a GPON network and an XGS-PON network into our coexistence element. Then we're connecting it into our fiber plant. And then the wavelengths from both of these networks now traverse all of the fibers behind it through our splitter and all of our outputs. So to illustrate this concept a little further, let's take a look at an existing GPON network here. So as you can see, we have a GPON OLT transmitting downstream to its GPON ONTs at 1490, and then all of our GPON ONTs are transmitting back upstream at 1310. So let's assume that we're beginning to saturate this link, this PON interface. We're saturating all of our available bandwidth. And we need to look at a migration plan to start moving customers over to XGS-PON. And we don't want to do a rip and replace. We don't want to cut all this out and install XGS and replace all this. That's going to be way too expensive, time consuming, and not to mention the impact it's going to have on our subscribers. So what we want to do is we want to overlay XGS-PON along with GPON. And then we want to only move, maybe we only want to move individual ONTs. And we want to start with maybe this guy, this subscriber. This guy's a big talker. He's the one that's really sucking down my bandwidth. So I want to get him off of GPON. These two, I'm not in any hurry to move them. I may decide I'm going to leave them on GPON. And maybe at a later date, as they increase their bandwidth, then maybe we'll move them over to GPON. So the way we want to do this is we want to install a coexistence element right here between the GPON OLT and our plant fiber, and then we're going to install an XGS OLT and tie it into our coexistence element. And when you do that, this is what your finished product looks like. You can see here we have our coexistence element in place. We have GPON and XGS-PON tied in, and both network wavelengths are traversing all of our fibers. And as you can see here, we've replaced our big talker with an XGS-PON ONT. So the reason that this works is because all of these ONTs have optics that are built to only receive at their given wavelengths. So a GPON ONT is only looking for 1490. The fact that 1577 is also coming down this fiber is irrelevant. It's only going to look for 1490, and it's only going to communicate at 1310. So it continues to communicate with its respective OLT upstream. And our new XGS-PON ONT is hard-coded at 1577, and it's transmitting upstream at 1270. So this gives us a very easy way of migrating technologies from a lower bandwidth technology to a higher bandwidth technology. Now we can come through and cut these ONTs over at any point we want, and we don't have to go out and change our fiber plant or do a rip and replace or spend a whole lot of money doing any of that. So does that make sense? Or any questions on these overlay networks or how coexistence element operate before we go into the next section? All right. So the future of PON. So the question is, what comes after XGS PON? XGS is where we're at today. Where are we going? Where do we think? What do we think that the next PON technology is going to be? Well, there's two on the horizon that I want to cover here. The first PON technology is called 25 gig. 25 gig is a symmetric PON technology, 25 gig in the downstream, 25 gig in the upstream. Something I would like to note about this technology is not being developed under an ITU standard like the other PONs that we've talked about to this point. This is actually being developed by a group of vendors and operators known as the 25 gig PON multi-source agreement group. Something that is a little bit of note here, and we're going to get a little deeper into this after I cover 50 gig, but let's take a look at the wavelengths. The wavelength, the downstream wavelength for 25 gig PON is 1358 nanometers. But you can see here there are three options available for upstream waves. So let me talk about 50 gig and then we'll come back and we'll talk about why this is compelling. So 50 gig PON is also symmetrical, offering 50 gig PON downstream, 50 gig bandwidth upstream. This is using fixed wavelengths, 1342 nanometers in the downstream direction, 1286 in the upstream direction. So the reason that these upstream wavelengths for 25 gig PON are compelling is because if a service provider was looking to migrate to 25 gig PON, and these are the three that they have to choose from, a lot has to be considered here. The type of network that they're running today, if they're going to overlay it, and the type of network that they plan to move to in the future. So look at the first one, 1270. Well, from the previous slide over when we were covering SGS PON, you'll remember 1270 was our upstream value there, right? So if you were running XGS PON today, and you were thinking you wanted to move to 25 gig PON, you would not be able to use 1270 because that's already being taken by XGS PON. So let's say that whenever you migrated to XGS PON, you overlaid it on your GPON network, and maybe you've got some GPON nodes that are still out there in your network today. Well, 1300 is one of the three upstream wavelengths that are available. Well, this is a subset of GPON. GPON and EPON both use 1310, so 1300 is not going to work either. So that would force you into using 1286. Well, I just told you that 50 gig uses 1286. That's a fixed wavelength. So if a service provider was just adamant that they wanted to migrate from XGS to 25 gig today, and they had GPON deployed already as well as XGS, they would be forced to use 1286. And the problem with that is if at some point down the road, that service provider wanted to migrate over to 50 gig, they've shot themselves in the foot. There's no good way of doing it because they've utilized that upstream wavelength that's available to them on 50 gig. So these are some of these are some of the considerations that service providers need to think about as we start looking to the future of which of these two technologies to take. Because if you use this 1286 and you can't get the 50 gig, you might find yourself in a position where you have to wait for the next technology to become available after 50 gig, which could be years later, and then you just have to make 25 gig work. So that's the end of my slide deck. Are there any questions on anything I've covered?
Thanks, James. Great presentation. Checking the chat. If anyone does have any questions, throw them in the chat or come off mute and ask. Yeah, not seeing any at the moment, James, but just want to thank you. That was a great presentation.
I either confused everyone or explained it very well. So if anyone has any questions, Jason, feel free to relay those on to me. I'm happy to talk to anyone that might want to discuss this.
Yep, will do. Thanks a lot, James. So Stefan is the Director of Global Technical Sales with Tirana Wireless. He is regarded as a wireless technology expert with decades of experience in research and development, field engineering, and customer engagement. He has been with Tyrannus since 2021 and previously held senior director level positions at multiple wireless companies. So, Stefan, I'll pass it over to you and go ahead.
Yeah. Okay, guys, I know you guys had a long day, and to make this a little more interactive, feel free to add questions into the chat, interrupt me. Let's make it interactive, keep you all awake, because I have been listening for a couple hours to the great material that was offered to you guys. So hope I can live up to the standards the others have set. Why does fixed wireless access exist? And we are around because the digital divide problem still persists. What we find is that 40% of the world still has no fixed broadband in any form. That means no fiber, no DOCSIS connection, no high-speed DSL connections, which is VDSL, which can deliver the 100 meg. So there is nothing that they have, and we're trying to solve this gap. Fixed wireless access networking is a last mile technology that bridges a gap somewhere in the gap between, the internet backbone, the fiber to the home, and fiber to the home is a great technology, but at some point fiber to the home makes no economical sense, and that happens when the homes get further and further apart. So when you go into the suburban and rural areas, it becomes harder and harder to make economic sense of the fiber. Fixed wireless access devices, in contrast to mobile wireless access devices, run on the utility mains. An average home in the US is consuming somewhere around 650 gigabytes of data a month. A mobile user is using somewhere around 15 gigabytes a month. So it's a very different proposition to provide service. And that tells you also why doing it over the mobile network is not really an economical solution, because the home user is using so much more data. So fixed wireless access has an antenna on the outside of the house. It is fixed, therefore it's not moving, and provides high-speed service that is similar to a fiber connection in all regards that the end user can see. Mobile network operators provide data to your cell phone, and you watch low-resolution videos on there, and you browse, you do some navigation, but at the end, it's all much lower data rates than what we're doing right now, video conferencing, watching movies, and the like. Why is fixed wireless important? It is really the essential tool in bridging the digital divide. That means getting service to everyone. It is ideal for providing broadband access to remote areas. The radio frequency link for the last mile avoids digging or installing fiber optic cables. As I said, if you're in a city and homes are close together and you get a 30% take rate, this is still all very nice. But if you are in an area where everyone sits on a 1 acre lot and from home to home you have half a mile, and then you get 30% take rate, deploying your fiber cable, you will never make back your investment. You have high operating cost, and you don't want to do this because your company doesn't make money, and if it doesn't make money for too long, you're not going to be around. So you're looking at what other infrastructure is there. And what is there is cell phone towers in most areas, or in some areas you can put a pole into the utility right-of-way area. And on those, on that infrastructure, you can install fixed wireless access to connect these homes. And the beauty here is that you are not building a connection to each home unless that home buys service. Then you place your antenna on that home and provide the service. So you have no upfront cost and no maintenance cost in the areas where you're not providing services. Other things that we find is that in historical cities, opening up the street to dig fiber takes years and years in permits. You have century-old apartment buildings where it's really hard to make connections, go through the walls. No one knows where the cables are running. And in these instances, fixed wireless access might also make sense. The fixed wireless access system begins with a tower, a building, an endpoint. You know, if you have a head-end building that is tall enough at the edge of the city or a neighborhood that is sparsely populated, those are all good locations to place your base nodes for your fixed wireless access system. The signal is then processed by a modem with a router. That can be any standard router that you buy today, home access router. That can be one of those Calix routers where on one end you put Ethernet in and then Wi-Fi covers the home. Or it can have multiple Ethernet ports, a wide area network port, and then wiring in the building. But today, pretty much everyone runs everything wirelessly in their house. And that is the most common way. Today, many of us have used our mobile phones as hotspots. But when you do that, you notice quite quickly that your phone gets hot, empties the battery quite quickly, and that the speed is limited. According to a study from Nokia, when you're doing fixed wireless access with mobile devices or indoor devices, you're losing roughly 1/3 of your network capacity to inefficiencies from penetrating walls. And that is a very high price to pay if you then connect users that use the 650 gigabyte per month, because that is like transferring a terabyte of data where on the mobile network, you typically, as I said, you see 15 to 20. Many technological advances have made fixed wireless access a much better solution today than it was just 10 years ago. We have completed MIMO, which means multiple inputs. That means multiple antenna passes are used at the same time, or MU MIMO, which means multi-user MIMO. All these technologies have been improved vastly over the last couple of years, and therefore the performance of fixed wireless access has grown much faster than the performance of other technologies. But that is simply because we started from a lower base. What makes up a fixed wireless access system? A cell tower, a high-rise building, a utility pole in the right-of-way, a wireless connection, then a receive antenna, then you go into your CPE device that then either puts Wi-Fi connections out inside the home or wired connections, whichever model you choose to use there. The big question is, what are the pros and cons? The pros are it's quick and affordable to install. You don't have very long permitting processes because you don't need access to utility poles or bury fiber in the ground, which means permits from the city, the county. You're crossing one of the administrative lines and you need to repeat the whole permitting process. And you can very quickly extend the coverage into the rural areas around the city and provide uniform service in the rural areas close to your city. So it's a very quick solution for you to expand the footprint of your network. It bridges connectivity gaps. You don't need a phone line. No other internet connection is required. It's much lower latency than any of the satellite services where they have their place. That is one of the things that when you always ask somebody about their technology, they will tell you that their technology solves all the issues. But the reality is that all the technologies that are presented to you are tools in your toolbox. There is a place where you run fiber, there is a place where you run fixed wireless access, and in the super rural areas where you have these homesteaders that are tens of miles from the next connection point, that's where you clearly use a low Earth satellite connection because it's the most economical solution, and those users will be able to, or will have to, in the absence of any other technology, accept the higher latency. Some people still believe that fixed wireless access needs line of sight. I have been asked to make this a general technology presentation and not too much about the company. At some point, I will have to talk about Tarana as a company because we no longer need line of sight, but most technologies that are available in the fixed wireless access space today require line of sight between the endpoints. Some technologies that are being deployed right now can potentially be impacted by weather. Let's put it this way, if you look across the spectrum, the higher the frequency, the more susceptible you are to weather, and the low frequencies are more susceptible to multipass, and the crossover point is somewhere at 10 gigahertz. If you go above 10 gigahertz and you're weather impacted, and if you go below 10 gigahertz, you're multipass impacted. And there are nice standardized models that you can use to calculate the impact, so you can make very good predictions there, and that helps out. It has higher average install costs than the indoor self-install solutions. If you send a technician out, then you have a higher cost here, but you're regaining network capacity, performance, so there is a trade-off to be made. And naturally, the available radio frequency spectrum is limited because most of it has been assigned to different services, and every service is clamoring for more access and to spectrum. And then we have general security and interference issues. People say, hey, it's wirelessly, it's in the air, everyone can pick it up. And we all know that is no longer true today. Most technologies today run encryption over the air, and newer technologies have very good ways of dealing with interference from other devices running in the same spectrum. What we see in the fixed wireless access world is that people are using Wi-Fi devices which are designed for indoor, and they're trying to use them outdoors. And that quite often leads to disappointing performance because Wi-Fi is a great technology for indoor, but one of the key tenets of Wi-Fi for its great performance is that it runs on protocols that rely on listen before talk. That means that all the devices can hear each other and only one of them transmits. And when no one transmits, you can fill in the gap. Now we are going outdoors to longer distances and we put directional antennas on these devices. They can no longer hear each other. So they are talking over each other, then they're doing random backoff, and the more users you put on, the less throughput you get. So the exact opposite of what you wanted to achieve. Only the access points have intelligence is the other weakness of Wi-Fi. That means only the access point can direct energy to a remote node. The remote devices are dumb. The access points today have enabled MIMO, and if users are sufficiently separated, we can have multi-user MIMO in Wi-Fi. But as I said, it's mainly an indoor environment, and the support for non-line of sight and near line of sight outdoors is missing. Indoor, the effects of reflections and multipass are so small that they don't impact performance, because you just cannot create huge differences in time of arrival when your transmit distance is 30, 40 feet. The other solution we are seeing quite often, and I will take this slide away, is that the 3GPP or the mobile networks are used for fixed wireless access. And the problem with the mobile networks is that they are inherently designed around a handset, and a handset is battery powered. So you're trying to ensure that a battery lasts at least 24 to 48 hours. And what's the standards that 3GPP and 4G and as well and 5G and R have said is, on the uplink, we are using less time for the uplink, and we are using lower order modulation, so we don't need as much transmit power, so our batteries last longer. So you now have a network that is very heavily directed in the direction of the consumer, where the end consumer is the receiver of data, but it's a very limited upload capability. 3GPP is the best solution there currently is for mobile. It's a great standard. It does mobility very well. What you see is that we have lots of mobile users, and more mobile connections are made continuously. It's like many of our cars today are continuously connected to mobile networks to exchange traffic data or do other things, but these are all relatively low data rate data. What we are seeing now is happening is that there is a mix of technologies, and when we see what we see here is that we get very limited throughput, and that has been addressed by adding more and more devices, which creates more and more interference, and overall network capacity is dropping. And we need new technologies to address those problems, where fewer devices can serve more customers, and that will allow us to bring more capacity into an area so we can provide a more unique service to customers that feels like fiber. The low Earth satellite solutions like Starlink are great once they are new or the area is not densely populated. So if you're in a super rural area, you are going with a low Earth satellite solution and you will get fantastic results. But what people have found is that they decided to buy this in the city because they like new technologies. They wanted to use the same internet connection for their home as they are using for their RV when they go camping. And in the more densely populated areas, the throughput of these solutions has suffered significantly, because you are shooting a large area up to a single satellite, and this single satellite then shares the bandwidth between all the users. And naturally, if you are in outer space, and we said that higher frequencies are more affected by weather, that means by definition you shoot through the clouds and the rain for the whole distance. So you get attenuation along your entire path. And that means you get very highly affected by this and see lots of performance degradation in weather conditions. And the reality is, when do we want to watch a movie? not when the sun shines outside and we're doing a barbecue. We want to watch a movie when it rains or it snows and we can't do anything outside. So the problem here is that your connection speed is lowest when you want it to be the highest. And that is really the limiter for this solution in the more densely populated areas. Typical download speeds of different technologies are shown here. Naturally, these are average values, and each one of you can give me an example where I'm wrong. I'm fully aware of that. But on average, these are the speeds that are reported by the services that measure these speeds. And that is kind of what we are looking at across all the different solutions. And as I said, don't view this as one solution for everything. There is nothing wrong with having fiber to the home or DOCSIS to the home in a densely populated area. These are very efficient solutions. I don't say don't do that, do only fixed wireless access. We're at the edge of town where the homes are further apart.
Hey, Stefan, can I just add to that real quick?
Yes.
Just for the audience. So just like Stefan said, where the cable companies are really looking at this technology is primarily those rural, outside of our footprint type opportunities, which really is a result of federal funding like, RDOF in the past, the Rural Digital Opportunity Fund. Now there's BEAD, Broadband Equity Access and Deployment. So there's some federal dollars and subsidies that are being used by companies, including other overbuilders. But even the cable companies, Cox, Comcast, Charter, are using fixed wireless for some of those outlying areas where, just like Stefan said, and we all know, building fiber is very expensive, especially those really small rural areas. So that's where this really comes into play for all of us.
Yeah, perfect addition, Jason. And again, it's a tool in the tool bag. And again, don't get cornered by people that say it's like, we are only doing fiber. It is not the best solution for everything. Or we are only doing fixed wireless. It's not the best solution for everything. Now I have to tell you a little bit about Tirana, what makes us different and what is the goal that we set as a company. And one of the things that you will find is that there is currently no industry standard for fixed wireless access. So there is still room for large innovation. We have seen that there are other standards out there for wireless technology, Wi-Fi, which I'm connected with right now. This is a connection you have in your home, in businesses, when you go to the coffee shop, to the mall, in the airport. This is all Wi-Fi. And then you have 3GPP solutions, which are 4G LTE or 5G NR for mobility. And there's great standards out there where companies have gotten together. But in the fixed wireless access space, there's still a large variety of solutions that are all proprietary. Even the people that use Wi-Fi chipsets each one of them uses a different over-the-air interface that they have modified from standard Wi-Fi. So you couldn't buy units from two different vendors and have them talk together. That currently doesn't exist in the fixed wireless access world. I'm sure this will change over time. Like with everything, standards will develop and we will have multi-vendor solutions. But right now, fixed wireless access allows huge amounts of innovation. And with that in mind, Tirana has gone to say, what are the goals? And we said, okay, a fiber class per household speed, and that means at least 100 meg to every household, up to a gig. Low latency and support for symmetric uplink and downlink. Because when you're at home, and you're doing video conferencing, you have multiple people doing video conferencing in larger families, you're creating content, you need upstream speeds. And we needed to bring high capacity per neighborhood for an economically scalable deployment. So in the past, when more users connected, the throughput was dropping. We've said that's unacceptable. We need to have throughput scale with users. And we need solid connections despite obstacles in the way. And that's like other houses, trees, and vehicles moving on the street. Interference from other wireless networks. We must be able to overcome those. And we did. For those of you that are wireless nerds, there's an interesting ITU standard. It's called ITU RM2135. And that says that once you are 350 meters from a single family home, 90% of the connections beyond that are non-line of sight. So that tells you why line of sight technologies are too limited, because the coverage area becomes too small. You need too many backhaul points for the fixed wireless access, and you're losing the economic advantage that fixed wireless access was supposed to give you. And that's why you need a technology that can operate in near line of sight and non-line of sight. We need a consistent service quality. That means that the solution has to continuously update the way it operates to adapt to changes in its environment, so that a user doesn't get 200 megabit per second when he installs and a week after gets 100 and there's nothing that can be done. It needs to be 200 in the beginning, and it needs to be 200 a month later, a year later, or 3 years later. And this allows you to do marketing in a more efficient way, because you can make a prediction and say every home within 3 miles from my service point gets 200 megabit per second. You no longer need to do a design on a per home basis and make a different prediction for each home. Naturally, there are still differences, but if you give yourself some headroom, you can now provide a service that is smooth over a large coverage area. And we have worked hard on simplifying the installation. This is with antennas that do self-aligning, with a mobile phone app that helps the installer to find the correct direction and ensure that he's connecting to the correct tower and not pointing in the opposing direction. This tool also makes sure that you can now do capacity planning. So if you have a household that can see 2 towers equally well, you look at which tower is heavier loaded, and then you can point the service towards a tower where your load is lower. So you can, again, make sure that there is a more unified experience across the network. What we have done is we have developed products in the 3, 5, and 6 gigahertz band that can give you up to 3.2 gigabit per second per base node. You place 4 base nodes on a tower. We are putting 12.8 gigabit per second into an area, so we are reaching the capacity that you would have with an XGS PON from a single tower. In line of sight, that means no obstacles, so you're going to a relatively high tower, 120, 150 feet. You can shoot to homes that are 10, 20 miles away and provide service. Again, you're going into the semi-rural areas, not into the super rural areas. In non-line of sight, you get 2-3 miles of range for services that exceed 100 megabit per second. Each of these sectors can support up to 250 clients. Naturally, if you are selling 200 meg services, you don't want to have 250 clients on there. The number will be somewhat lower. You guys are all aware of oversubscription modeling, busy hour modeling, and those things are independent of the technology. You do this with your DOCSIS technology, you do that with your fiber to the home solutions, and you apply the same formulas to the wireless solution. Integrated massive MIMO antenna arrays on both ends of the link. That is truly the Tirana innovation. Huge computing power in there, no backend. It's a self-contained solution that as an output has a 10 gig Ethernet port that goes into your site router, where you can combine it with all the other traffic you're generating at the site and using the shared backhaul. We can transmit compatible with the LTE frame type 2 subtype 7. This is important in case you're renting tower in the CBRS band. You see that the mobile operators are using this to a large extent. And we can make sure, even so we're on different frequencies, that we transmit at the same time that they do and we receive at the same time. Therefore, the two systems do not interfere with each other, and we can adjust to their network timing. So this allows you to share infrastructure with the mobile operators, and both systems can provide high performance. The other big innovation that is coming to the industry is a frequency reuse of one, where all sectors can run on the same frequency, simplifying network planning and increasing the amount of data that can be provided in the spectrum that you have purchased. Many of the MSOs have purchased CBRS PAL licenses. And with the older technologies, you needed to say, okay, I've purchased 40 megahertz of spectrum. I use 20 megahertz north-south, and I use 20 megahertz east-west. With newer solutions, you can now use the 40 megahertz in all 4 directions at the same time. And the built-in interference cancellation technology in many of the newer products allows you to run the network there with minimal impact on throughput. The remote nodes that we are providing are, relatively speaking, small. They are pretty much a hardback book mounted to the wall, to the eave of the building, depending on the conditions of the link. We can have multiple network profiles where we have more downlink than uplink. And when you serve mainly residential areas, you will find that there isn't as much uplink as downlink. Even so, you could technically provide a one-to-one service, but we're a TDD system. That means we're using the same frequency uplink and downlink, but we transmit them at different times. And we can decide how much time we assign to each direction. Since the internet is still used in a 5 to 10 to 1 way at the residential homes, why not use more resources for the downlink, provide a better experience? And if you want to provide business services, then you would use a different network profile. So you have flexibility there. Again, it's your standard traffic planning that you're used to from other technologies. It's a single cable install. It's an Ethernet cable, power over Ethernet. So it's a simplified installation here. It's no longer power and Ethernet separate cables or fiber. These are standard cables that people are used to working with. And on the inside, the power is provided by a PoE injector that runs off the AC mains. But if you are providing voice over IP 911 services, you can also plug this into a UPS and provide phone services that will never go down. And you can design this to have the same amount of backup power that you have for your own central sites. Because usually power outages are over larger areas, so the CO most likely has the same power outage as the home, so the batteries don't need to last longer on the home than they last at the CO. One of the great innovations that has come is with the 6 gigahertz band is that we can now reach gigabit speeds in the downlink to the home with fixed wireless access. This is not only a Tirana thing. There is multiple companies that have 6 gigahertz products that allow them to provide gig services. And in line of sight conditions, we are seeing 3, 4. We have seen some field results that are better than the 4 miles that we're quoting on our data sheets. We have seen people having near gig speeds out at 6 miles. Excuse me. But this makes fixed wireless access a truly competitive solution with fiber to the home in the speed that we can get, and we are also approaching nearly the same latency. Not quite, but we are close. And this will allow fixed wireless access to be used in many more locations and provide a similar user experience. Interestingly enough, we have currently 110,000 homes connected with our technology, and we have a cloud-based management system out of which we can pull data. And what we are finding is that on the gig services, the majority of the users do not use any more data than the people that buy a 200 meg service. So somewhere after 200 meg, the internet is not providing any more useful data to the home. So the majority of people that buy gig services buy them as bragging rights, not because they really need it at their home. I have talked a lot about line of sight, non-line of sight, near line of sight, and many of you might have asked yourself, what's he talking about? And line of sight for quite a few people means I can see the other end, and that is visual line of sight. Radio line of sight works differently. If you want to have the mathematical formulas, I left them deliberately out. You can find them in Wikipedia, type in Fresnel zone. Fresnel was a French professor that in the late 1800s came up with a formula that said at this frequency, at this distance, the signal actually occupies a larger space than what you can see. And that's called the Fresnel zone. And if that is free of any obstacle, that is what you call radio line of sight. If you have obstacles in the radio line of sight, but you do not cover all of this zone, then you call this near line of sight, and that's what the second picture in the row shows. And if this zone of signal is completely blocked, you call that non-line of sight, and the signal now comes to the remote end through the gaps, through penetration, or via reflections. And these are the different access methodologies. And again, line of sight typically extends from the tower 300 to 350 meters. And after that, a large majority of links in fixed wireless access are near or non-line of sight. And this is simply based on the fact that we are not placing our equipment on a mountaintop far away from the city. We are typically on lower installation points near the users, near the villages and towns that we are covering. And therefore, it is important for us to be able to work under all link conditions. I will show you an example of what is possible with wireless today. This is a sample shot that was done in New York City. And what you will find is that the base node and the remote node have no line of sight to each other at all. But cities have lots of reflective surfaces, of which signal bounces off and finds many multiple ways to reach a remote node. The beauty is that when during the Calix presentation, you saw the signals not being able to distinguish. Well, there is multiple wireless technologies today that can distinguish between the different multipasses because they have multiple antennas. Each antenna receives one direction and then is able to recombine those signals. And as I said, Tarana does this, but there are other companies that have different algorithms that do that, but have a similar outcome. So this allows wireless today to operate in far more challenging environments than it has historically been able to. And if you want to know what is reflective, again, below 10 gigahertz, buildings, smooth surfaces, roads, lakes, streets, those things are reflective. And if you go with a high frequency solution, the signal is not being reflected, is actually dispersed because the wavelength is so short and it gets lost in all directions. The other big step forward is the avoidance of self-interference. What you see on the left graph here is that you needed two different frequency pairs to serve users that were close by each other. And now with beamforming, you can have the same frequency serve multiple users. This is again a first in the application to fixed wireless access, but it's not a unique thing to Tarana because the base station in 3GPP also does beamforming to ensure that the maximum signal level gets to your mobile device. The problem in the 3GPP solution is that your mobile device has no such intelligence and has an omni antenna that puts signal in all directions, and that limits the uplink capacity, and that's why the mobile technologies struggle with uplink. In the Tarana world, the remote nodes can also do beamforming. And this beamforming in both directions allows for optimum connections, optimum frequency use, and allows you to have a frequency reuse of one in neighboring cells, each getting a unique data set on the same frequency at the same time. What is MIMO? I have used the term multiple times just to make sure we're talking a little bit about these industry terms. MIMO means that we're doing spatial multiplexing. We have multiple inputs and multiple outputs. This takes advantage of multiple radio chains at both ends of the link. You have solutions that have two transmitters, two receivers. That is typically one is vertically polarized, one is horizontally polarized, and that has been around for a long time. And then we have the larger MIMO solutions where we have 4 transmit chains, 8, 16, 64. These solutions allow you to decide when to energize the transmitters so that the energy adds up in a specific direction. And that is what makes MIMO such a powerful way that has pushed capacity in fixed wireless access systems up massively. The next step up from just MIMO is to have distributed massive MIMO. That means both ends of the link have multiple antennas. So here we're showing a solution that has 16 at the base, 8 at the remote. So you have 16 times 8, 128 different combinations that you can analyze and recover at each end. And these multiple combinations allow you to combat the impacts of path fading. If you come from the point-to-point microwave world where fading was a major issue, you then had what was called either frequency diversity, where you used 2 frequency on the same antenna with 2 radios in the hope that only one of the frequencies was impacted, or you would have a second antenna that was placed a couple of wavelengths away, and you were assuming that you would get different reflective points at different times of the day, and that this would allow you to keep a connection up at all times. Here we're doing this on a massive scale continuously, and that is really a big technological step forward. The other thing that beamforming brings is that we are no longer sending energy in all directions. We are only transmitting energy in a direction where it is needed. This means that if somebody else shares the tower and is transmitting in a different direction, we can use the same spectrum at the same time without harming each other. And the solutions that we are looking at today are built after the example of the resource block that was part of 3G and GSM, pushed forward with WiMAX, and now is present in 4 and 5G, where we say we are not transmitting all our spectrum to a single remote node. We're using part of the spectrum for part of the time, and we're assigning this dynamically so that we can have a lot more users using the same spectrum at the same time. This is a solution in Idaho where you had a rural area with no connectivity other than the mobile devices, which, given that it is in Idaho, lots of trees, had very low performance. And here, a partner of ours has deployed this network with government funding, with outdoor funding in this case, and finds that the majority of the users now gets over 200 megabit per second. And there's just 1.8% of the locations that are not covered. Those are homes in valleys. But this is a way where the rural communities can cross the digital divide for a much lower cost than fiber, and more importantly than the cost. Because you could say, okay, instead of a 3-year payback, we look at a 10-year payback and we still run fiber. The problem is that it would take many years to roll out this fiber network to these rural locations, where this was done within 6 months. This is another one, Sedona, Arizona. Again, not the household density is not too high. So in the core of Sedona, naturally, yes, you are running fiber, but again, Sedona is a largely spread city, spread over wide areas, and therefore there is many areas where fixed wireless access makes sense, and it is a much lower cost solution than going after these remote places with fiber. And as I said, one of the key things that we are telling you is fixed wireless access is part of a toolbox, and it is not the only solution or the best solution everywhere. At some point, when it becomes dense enough, you want to run fiber to the home, because there the upgrade path that Calix showed to 50 gig is really really more cost efficient. But if we are looking into the rural areas, what we are finding is that the cost for the rural areas is simply too high with fiber, and we are a nice addition to your toolkit there. And as we said, fiber is awesome. I will never tell you not to do fiber because it would just be wrong. But sometimes it's just hard to do, too costly to do, and make us part of the toolkit, or make fixed wireless part of the toolkit and ignore that there is Tirana because there's other solutions out there. Again, we were asked to talk about fixed wireless access and not too much about Tirana. I hope I limited myself. But our marketing team that made the slides for me put quite a bit of Tirana content in there. With that, let's open it up for questions.
Yeah, Stefan, that was a great presentation. I think you did a great job going over just fixed wireless technology in general. I mean, I honestly, and going into the Tirana specific stuff too, I didn't even realize like the non-line of sight was even an option for fixed wireless. So that was new to me. Good stuff. Any questions out there? I might have one or two, but let me see if any of the attendees have any questions.
Jason, it's quite interesting because our system tells us what the link distance is, and from there we can calculate if a link is line of sight or non-line of sight. And 80% of the links that we deploy today are either near or non-line of sight.
Yeah, that's very interesting. Years ago, I worked at the Best Western corporate office doing network designs for all the hotels, and you know, you said Wi-Fi is it's not good outdoors, and I 100% agree because we used, you know, Wi-Fi or wireless point-to-point, you know, antennas and everything to try to get between buildings, and if there was a tree branch in the way, well, we had issues. So.
Yeah, again, it's a technology that has its place. As I said, it's like my connection to you right now is via Wi-Fi. Most laptops no longer have even an Ethernet port, but it has its place. And when you try to bend it to do something that it was not supposed to do, it's like when you take your convertible to go off-roading, you're usually getting in trouble.
Yeah. So, question for you. I know today, you know, with your technology today, you can get a gig to a house. What do you see? Are there going to be any major improvements in future years with fixed wireless, or where do you potentially see some of those speeds getting in the future?
So we see a continuous path of improvement. We started selling products 3 years ago. Then our aggregate up and down link was limited to 800 meg. This year we're hitting 1.6 gig, and by 2026 we believe that we can have 3.2 gig services to a single home.
Oh, nice. Right, Eric, I see you have your hand up. Just unmuted you. So go ahead.
Yeah, I wanted to thank you, Jason, for giving us the time to present. And like Stefan said, I tried to make it not too much about Tirana specifically, but I did want the people to understand, because we are talking to so many MSOs. And by the way, I'm Eric Martin. I'm the account executive for MSOs for Tirana. I wanted them to understand, because they're going to start to hear our name a lot. I believe we're either in labs or POCs or whatever with most every major cable company, a lot of the small ones too. So I wanted them to understand why we're a little bit different than the wireless that they've had in the past that maybe didn't live up to expectations. So I tried to not to make it too much of a commercial, and Stefan skipped a couple of things I left that might have been too Tirana commercially, but appreciate you letting us talk. That's all I wanted to say.
Yeah, no worries. It was a great presentation. All right, I don't think we have any other questions, Stefan. So just wanted to thank you again. Great job.
Yeah, my pleasure. Hope we get an opportunity at some point to repeat this. And I'm impressed that you can keep 50 people on the line for 4 hours.
Yeah, sometimes we kick around ideas of different formats or maybe a shorter monthly. We've stuck with this 3 to 4 hour quarterly for a few years. Might change it up, but yeah, it's worked pretty well. All right, well, thanks everyone. With that, we'll wrap up our Q2 technical session. So if you do have any questions, feel free to send them to me. I'm Jason Bishop. If you don't know, Krista Thompson, just reach out to one of us. I do think we'll be sending out some follow-up emails and probably some LinkedIn posts as well. So just be on the lookout. All right, thanks everyone.
Mm,
Bye.
Thank you.